We have already seen a standard Turing machine. A standard Turing machine will look at an input and it will either go to the right or to the left, and if it needs, it might change the symbol and change the state from one state to the other state. That is what we have already seen about the standard Turing machine. Now, apart from this standard Turing machine, we could add we could modify it, and then we could see whether the power means, by talking about the power of a Turing machine, I mean to say the languages accepted by the Turing machine. So whenever I am talking about the power of a Turing machine, please keep in mind that what I mean to say is the number of languages accepted by the Turing machine. That is what is the power. So power of any machine is given by the number of languages that the machine could accept. For example, PDA powerful is, the power of PDA is it could accept many of the languages, but then it cannot accept A power n, B power n, C power n. But Turing machine, on the other hand, we have seen that it could accept A power n, B power n, C power n, and it could even accept A power n, B power n, C power n, D power n. You could extend it to any long, isn't it? We have already seen it. And now, by talking about the power of the Turing machine, what I really mean is not the time complexity or space complexity. What I mean is the number of languages that it could accept. Now, already standard Turing machine, which we defined earlier, is already able to accept some of the languages. Some languages it is already accepting. Now, by giving this Turing machine some extra facilities or some more modifications, let's see the resulting Turing machines, will they be able to accept more languages compared to the standard one. But then it has been found out that even if you give more power, even if you give more facilities or more modifications to the standard Turing machine, still the number of languages which were accepted by the previous standard Turing machine are remaining the same, which means even if you change the standard Turing machine to some other new Turing machine, the languages which are accepted by the standard Turing machine are only accepted by the new machines, which means by doing any modifications, we are not actually able to increase the power of a Turing machine. That is what we concluded. So by the theoretical proofs, what people have found out is by increasing the by doing some modification to the standard Turing machine, we are not able to accept any new languages which are not accepted previously by the standard Turing machine. Whatever were accepted by the previous machine are now accepted by the new modifications. In fact, some of the modifications are actually reducing the power, not increasing the power. But for now, we shall discuss what are the Turing machine modifications after which the power remains same. Okay, so let's see some of the modifications for the Turing machines here. First one is, see this Turing machine with stay option. So generally we know that the standard Turing machine will either move to the right or it will move to the left, and then it will change the symbol. But then if you give the power to a Turing machine that it need not move to the right or left, it can even stay, which means along with that these are all the standard modifications to the Turing machines. So first modification is, to the Turing machine I am giving you a stay option, which means if you are in some particular state, your transition function will be, and if you look at a stack, that tape symbol, you will go to some particular state, we are going to go to some particular state, and then we could change the symbol, and now generally the standard Turing machine will move left or right, isn't it? But along with that we could add stay symbol, stay option. Stay option means you need not always move, you can stay at a point and you could just be there, right? If even after adding this option, we found out that the power of the original Turing machine, the standard Turing machine, cannot be improved. Therefore, even a Turing machine with stay option is as good as a Turing machine, standard Turing machine. So that is what we found out. And now next look at the next one, Turing machine with semi-infinite tape. Semi-infinite tape means I told you that standard Turing machine has both sides infinite tape, which means if you are having A, B, C as the input, the standard Turing machine has both sides infinity. That is what we already know, right? Now, a Turing machine with semi-infinite tape means it is not infinite both the sides. it will be infinite only one side, which means you cannot move to the left beyond some point. That is not possible, you will fall off the tape. So we found out that by restricting the Turing machine to semi-infiniteness, which means you could move only to the right, not to the left, still the power of the Turing machine, the standard Turing machine, it didn't get affected, which means a Turing machine with semi-infinite tape is as good as standard Turing machine. It is not able to accept any more languages, neither it is accepting less languages. So this is equivalent to the standard Turing machine. And next one is offline Turing machine. So what is offline Turing machine is, we have till now seen that both the input and output are present on the tape, and now the Turing machine has a right that it could modify the input. But then what you could do is, you might not want the input to be modified, then you could have a restriction that, or you could provide the input in a separate file, and now our Turing machine will look at this file and then work on the tape. So which means you have the Turing machine. Now to the Turing machine I will give the input in a separate file, input file, and now this will contain the tape. Okay, now we are going to have this input which is read only. So our finite control of the Turing machine can read the symbols from the input and then it could write it there. So it could either read or write. It is read write only. So if this is the facility given, that is called offline Turing machine. Offline Turing machine means input is given in a separate file. So you are supposed to read the input from a separate file and you are not allowed to modify the input. In case if you have to do some modifications on the input, then you have to first copy the entire input onto the tape and then do the modifications on the tape. But even after your computation is over, the input is going to remain intact on the input file. It is called offline Turing machine. So by having such a kind of arrangement, still we found out that this Turing machine is as good as standard Turing machine. Okay. And next one is multi-tape Turing machine. Multi-tape Turing machine means we are going to have lots of tapes, not just one tape. So with single tape it is called standard Turing machine. Now if I give you many tape, that is called multi-tape Turing machine, which means I will have the finite control and then I will have lots of tapes and I will have read write heads with that. Okay, now this is called multi-tape Turing machine. So what is the transition function is, you will be in one state and then you will be looking at n symbols. So this small n is number of tapes you have. So in this case, if you have 3 tapes, you will be looking at all the 3 tape symbols. Then you will be going to some state and you are going to write there on the n tapes some symbols that is given by this, and then you are going to either in the n tapes you are going to independently move left or move right. Try to understand this. You will be in one state and you will be looking at n tapes, that is by tau power n, which means tau power n is nothing but from each tape you are going to look at one symbol. Therefore how many symbols are you going to look? N tapes, n symbols, right? And now using this you are going to go to one particular state, and in that state you are going to modify this tape symbol to something tau power n, and then you are going to move either to the left or to the right on every tape, okay, independently. It is called as multi-tape Turing machine. And again it has been found out that the standard Turing machine is as good as multi-tape Turing machine. Whatever are the languages accepted by standard Turing machine, they are accepted by multi-tape Turing machine. Multi-tape Turing machine is not going to add any more power to the standard one, which means to the standard one, even if you give it many tapes, it is saying that I am as good, I could do the same work with a single tape, like even if you give me more tapes, I will not be able to accept any more languages. But then it is interesting, even though the power of a Turing machine is not affected, but there is something different. In the sense, I told you that we are comparing the power of the Turing machine by using the number of languages, or by using the languages accepted by the Turing machine. But then by using these modifications, sometimes the time taken to accept any string may be different. I'll just give you an example. Even though both are having the same power, remember that multi-tape Turing machine and the standard Turing machine are having the same power, no doubt in that. But then it could do something better for some languages, in the sense the number of steps required to accept a particular string of some languages might improve using the multi-tape. So you have seen this a power n, b power n, isn't it? Now if I have the input a, b, 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 then how does the standard Turing machine accept it? It is going to go back and forth. So how is it doing it? Make it x and then go front, make it y, go back, and then go like this, and then so it is going to move back and forth a lot of times. But now if you have multi tapes, if you have more than one tape, you need not move back and forth these many times. You could actually do it in a better way. So in this one, if you just think about the time taken, so in order to accept a power n, b power n, if I have a so on, and then b so on, a power n, b power n, then the number of steps required in order to accept is, in order to just match 1x, 1a with 1b, we have to move actually n times, I mean n cells, isn't it? So in order to match up with one pair, the time taken is n steps. Then how many pairs we should match? N pairs. Therefore time taken is order of n square, or the number of steps taken is order of n square. But if we have a multi-tape Turing machine, what we could do is, let us say I have two tapes. Now on one tape there is a, b, input is given. Then initially what I do is, I copy the entire input to the other tape. So I'll just copy I'll just copy input to the other tape, which means I'll just copy a, b onto the other tape. Then what I will do is, in just one row, I mean in just see, for copying it is going to be order of n time. You just scan it and then put it there, and after copying it, just set this to here, one read write head to here and one read write head to here, for which time taken is order of n. And you can just simply scan one symbol here, one symbol there, one symbol here, one symbol there, which means in linear time you could actually match them. So by using multi-tape Turing machine, we could actually decrease the time taken in order to process some of the languages. It is true with any Turing machine with a modification. So the power in terms of number of languages accepted is going to be same, but the time complexity required to accept a particular language, that might vary. But that is not going to add any power, because we are defining power in terms of number of languages but not by the time. So every modification is going to be beneficial for some languages, but then overall put together, the total number of languages accepted, that doesn't change. Okay, so remember that even the multi-tape Turing machine is as powerful as the standard Turing machine, or standard Turing machine is as powerful as multi-tape one. Okay, and next one is jumping Turing machine. So jumping Turing machine means, till now we have seen that the read write head might move only one step ahead, either to the left or to the right. But now jumping Turing machine, instead of just moving one step ahead, it could in one go move many steps, which means if you have any input like this in the tape, you will be standing here. Generally our standard Turing machine moves only one step to the right or one step to the left, but then this jumping Turing machine can directly jump to any number of steps to the right. So to the transition function, one of the argument is also going to be the number of steps you want to move right or left. In our standard Turing machine, you know that delta is, you will be in one state and then you will be looking at the input, and then you are going to make a decision about what is the state you want to go and what is that you want to write on that input, and then you are going to have either to the move to the left or right, isn't it? Along with this move to the left or right, you could even specify the number of steps, some number n. So you can even move to the left or right, not just one step, you could jump n number of steps. So if you give it as 3, then it is going to jump 3 steps. Again, it is found out that the standard Turing machine and this Turing machine both are equivalent in power. So it is not going to add any more power. Okay. And next one is non-erasing Turing machine. Non-erasing Turing machine means till now we have seen that our standard Turing machine has a capacity to take an input, and in place of that input, let us say if the input is 0 or 1, in place of that input it could change it to in place of that input it could change it to a blank, our standard Turing machine, isn't it? But then if you remove that option, which means you are not supposed to change the input to a blank. If you remove that option, then it is called non-erasing Turing machine. The input, whatever is there, you are not supposed to write a blank on that. You could write actually any other symbol. So if you use that, that is called non-erasing Turing machine. Again, it is also equivalent to the standard Turing machine. Now, how is it equivalent is, so whenever I'll just tell you the proof. Generally, now till now we are saying that all these are equivalent. Then how are they going to prove it is, they will take one Turing machine and they will try to simulate the other Turing machine, which means the standard Turing machine, if it is having a transition function, then for every move of the standard Turing machine, there should be a move corresponding to that in the modified version. That is called simulating, which means if the standard Turing machine is able to do some task, the modified Turing machine should also be able to do that particular task. Now in our standard Turing machine, we have the notion of erasing. It can replace any symbol with a blank. But then non-erasing Turing machine is saying that we are not going to erase anything. Then how is it equivalent to the standard Turing machine is, we are going to use, instead of blank, we can use a different symbol, some other symbol. So instead of capital B, you can mark it as X. So that is not, according to the Turing machine definition, it is not a blank, but according to you, it is a blank. So if you use that, then it is nothing but we are not erasing it, but our task is done. So you know that X is a blank, but Turing machine thinks that it is not erased. Okay. And next one is always writing Turing machine. So our standard Turing machine, we have a restriction that, we have a liberty that if you are seeing a symbol, you can leave the symbol as it is. But always writing Turing machine means if you are looking at a symbol A, then you are supposed to definitely change that symbol to some other symbol B. That is what the standard Turing, this always writing Turing machine does. Now it can be proved that it can be this is not going to add any power to the standard Turing machine. How can we prove it is? I'm just telling you the proof, it is not required. How can we prove it is? They are saying that every symbol, whenever you visit it, it should definitely be changed. Then what you could do is, if it is small a, just change it to a capital A. But according to you, you know that capital A and small a both are same. But then the Turing machine thinks that, oh okay, it is changed, isn't it? You can cheat it. And later what you could do is, after entire your computation is done, again change it back to small a, isn't it? Therefore whatever result you wanted, you could achieve it, but then giving an illusion to the Turing machine that you are always changing the symbols. It is actually proven that it is not going to add any power to the standard Turing machine, which means standard Turing machine is as powerful as this always writing Turing machine. Now look at this one, multi-dimensional Turing machine. So multi-dimensional Turing machine means in our tape, instead of having 2 dimensions, which means left or right, we can even have we can even go up as well as down. So multi-dimensional Turing machine looks like this. It is not just having left and right, it could even move up and down. So let us say your finite control is pointing to a cell like this. Now from this cell, it can move left, it can move right, it can move up, it can move down, isn't it? So multi-dimensional Turing machine, you will be in one state, and upon looking at the input symbol, you can go to some other state and change that symbol if you want, and you could move left, or you could move right, or you could move up, or you could move down. So that is why it is called multi-dimensional Turing machine. And again, it has been proven that it is not going to add any power to the standard Turing machine. Both are equivalent. And next one is multi-head Turing machine. Multi-head Turing machine means it is having only single tape, but it can read from different places at the same time, which means our finite control, it can look at various places simultaneously and then it can take the decision. Again, it is proven that it is not of much help, so it is as powerful as standard Turing machine. And next one is automata with a queue. So automata with a queue means if there is a finite automata to which we are adding a queue, then that is nothing but that will be equivalent to the Turing machine. It can be proven that if the finite automata is given a queue is okay. Remember that queue is a much powerful data structure compared to the stack. If you have a queue, you could do more compared to what you could do on a stack. Okay, and it can be seen in data structures again. But anyway, you can remember that automata, when it is given a queue, it is as good as a Turing machine. And next one is Turing machine with only 3 states. It is very difficult to prove it. I mean, don't look at the proof. It is going to take a lot of effort to understand it. But then, if you could remember it, by heart it. So Turing machine with just 3 states is going to be as good as any Turing machine. How is it possible? We could design a universal Turing machine. I'll tell you that later. But anyway, I'm not going to prove it. So it can be proved that when people have already given the proof that a Turing machine, any Turing machine can be minimized. There is no algorithm, but then we can prove it. Any Turing machine can be minimized to a Turing machine which has only 3 states. Okay, so keep that in mind, and if you want to look at the proof, you might have to refer to some research papers. It is going to be very difficult. Forget, don't dig into it. Okay, next one is multi-tape Turing machine with stay option and at most 2 tapes. So if you have a Turing machine which is having multi-tape means you already know. Along with that, if it is having stay option also, then only 2 states are enough. Remember this also, don't dig into the proof. And now this is as good as standard Turing machine. So any standard Turing machine can be converted to a Turing machine with 3 states, first point. And second one is any Turing machine can be converted to a multi-tape Turing machine with stay option which will have only 2 states, at most 2 states. So it is very important, remember these 2 points. And proofs are going to be very difficult, don't dig into it. Next one is non-deterministic Turing machine. You already know that non-determinism means upon looking at one symbol and upon looking at if you are in one state and one symbol, which means you are in one configuration, you can make multiple copies of yourself, which means you can simultaneously go to many states and you could get many tapes and change the tape configuration, and also you can move to the left or right as you wish. So non-determinism is same as non-determinism in the finite automata. Now coming to finite automata, we have seen that DFA and NFA are both equivalent in power, and coming to push-down automata, we have seen that non-deterministic push-down automata is more powerful than deterministic push-down automata. But coming to Turing machine, here it can be proven that non-deterministic Turing machine and deterministic Turing machine both are same in power. Okay, it is very important, remember this, very important. So non-deterministic Turing machine does not add any more power to the deterministic Turing machine, so both are equivalent in power, but it is contrary to what has happened in push-down automata. Okay, now non-deterministic Turing machine is nothing but you will be in one state and you will be looking at the input symbol, and from there you can split yourself, which means you can make any copies of yourself. A 2 power is nothing but power set, isn't it? You can make any copies of yourself, and each copy can enter any state, and each copy can change its own tape. Every copy is going to get its own tape. Each copy can change its own tape any number of the way it wants, and then on its own tape it can move either left or right independently. That is called non-determinism. But still non-determinism is not going to add any power. Deterministic Turing machine is equivalent to non-deterministic Turing machine. Okay, very important. Deterministic Turing machine and non-deterministic Turing machine both are equivalent in power. Next one is a non-deterministic push-down automata. So to a push-down automata with two independent stacks. So you know what is a push-down automata. Push-down automata has only one stack. Now to the push-down automata, if you give one more stack, then it is as good as Turing machine. That is what they say. Okay, understand this. Automata with a queue or push-down automata with one more stack, which means with totally two stacks, they are as good as Turing machines. So see this queue, which means generally you know what is a non-deterministic push-down automata transition, right? You please refer to that non-deterministic push-down automata. Let me explain you this here. You will be in some state and you will be looking at the input sigma, or you will be looking at epsilon, and you will be looking at the stack configuration. This tau and tau are nothing but top of the stacks, and you will be looking at two stacks, two top of the stacks, and from there you could go to any number of, which means you can make any number of copies of yourself. Each copy can enter its own state q, and they can replace the top of the stack with any string they want independently. That is the independent meaning, which means you need not push the same things on both the stacks. If both the stacks are going to be dependent, which means whatever you are writing on one stack is going to be copied on other stack, it is as good as having only one stack, isn't it? But here both are independent. Okay, so remember this, whatever points I told you all here, I am not going to give you proof. Proof is going to be very difficult. In fact, for all the Turing machine concepts, I'll just try to explain you in words without any formal proofs. Formal proofs are not required. Coming to GATE, they'll just ask you the statements, not the proofs. For GATE, it is good enough. But if you want to learn more, maybe you might have to refer to the research papers where they have the formal proofs, and it is going to take hell a lot of time. But for GATE, just keep it simple. Understand whatever I'm trying to say. You just take a detailed notes of it and try to mug it up, which means read 2-3 times so that you will remember it. So in this, the most important point is deterministic and non-deterministic Turing machines are equivalent in power. Okay, fine. Now you might have got one doubt. The Turing thesis says that every Turing machine is as powerful as a computer, isn't it? That is what Turing thesis said. So every Turing machine is actually as powerful as a computer. But then what is a computer? It has a power to run any program. But then when I was designing these Turing machines, I was designing the Turing machines for a specific problem, which means a Turing machine which is designed to accept a power n, b power n cannot add two numbers a plus b. But our computer, of our digital computer, it will be able to add two numbers, as well as it will be able to do this, isn't it? So there is a basic difference. Our computer acts in a different way and our Turing machine is acting in a different way. You might have got that doubt. When I am saying that Turing machine is as powerful as a digital computer, our digital computer can do many things. So depending on the input program, the program which you give, depending on that, our computer will change its behavior. But then a Turing machine, once it is programmed, which means once I design the Turing machine, it is able to solve only one particular problem and it is not able to solve other problems. A Turing machine which is designed to solve a power n, b power n will not be able to solve a plus b, but our real computer does. Then how can I say that a Turing machine is as powerful as a computer, right? So in order to answer your doubt, in order to clarify why Turing thesis is right, we could do some other thing. So we are going to design a new Turing machine which will act as a computer. In the sense, I am going to design a new Turing machine which will take as input one Turing machine and then run that Turing machine inside this big Turing machine. Okay, it is going to be somewhat confusing. You have to really pay attention here. So what I mean to say is, I am going to design a new Turing machine which will act as a computer and which will answer your doubt and which will prove that Turing thesis is right. What is Turing thesis? Every Turing machine is as powerful as a computer. Therefore, I am going to really design a Turing machine which is as powerful as a computer. So that Turing machine is called universal Turing machine. Universal Turing machine means it is the biggest Turing machine. Okay. Now let's see how does this universal Turing machine works. A universal Turing machine is going to have a finite control, but then it is a multi-tape Turing machine. It is going to have 3 tapes. It is going to have 3 tapes. let me call one tape as tape 1, and other tape as tape 2, and the other tape as tape 3. So it is a multi tape Turing machine, and you already know that multi-tape Turing machine is as good as a standard Turing machine. Then why am I taking multi-tape Turing machine? Is it is, you know, it actually simplifies many things. That is the reason. So in order to implement a multi-tape Turing machine using a single tape Turing machine, it is going to be difficult or complex to explain you how it works. But if I take a multi-tape Turing machine, the explanation will be very straightforward. Now this is entirely a one Turing machine. I want to use this as a computer. Then if it has to be a computer, then it should be able to do any generic work. So what I do is, for example, if I want to add two numbers a plus b, then what I do is I design a Turing machine separately. I'll have a Turing machine separately, and which is written actually to add two numbers. So what will that Turing machine will have? That Turing machine will have a finite control, and along with that it will have a input tape, and on this input tape you are going to put what are the two numbers you are going to add, right? So the two numbers are, let us say, 2 plus 3. Then I am going to represent 2 and I am going to represent 3, and now I want to add it. And now this this Turing machine is going to be designed the way we have already seen it. So this is some other Turing machine, the normal Turing machine, and that is universal Turing machine. Now what will this universal Turing machine do is, it will take this Turing machine and it will store the Turing machine in its one tape. Therefore this tape T1 contains representation of some other Turing machine. Okay, and now what about the input? The numbers, whatever is the input given to the original Turing machine, that input can be saved in the second tape of the universal Turing machine, which means here I am going to put the input, actual input, right? And this tape 3 is used for the rough work. Rough work means, now what we do is, this universal Turing machine will trace out this small Turing machine on this input. While tracing out the Turing machine on some input, what is that we are supposed to remember is what is the present state we are in. So here it is going to save the internal state, which means initially internal state will be Q0. You know, if you assume that let us say initially the internal state is Q1, if you assume that this Turing machine is going to start with internal, initial state as Q1, then Q1 will be in this tape, then input will be here. Now you will see Q1 and you will see the first symbol of the input. Then you will go to the representation of this Turing machine and you will see for this configuration, which means what is the configuration? Q1, and for the input let us say 1, then delta of Q1 comma 1, then it will go and consult this Turing machine representation to see what should be really done here. Now let us say this Turing machine representation is saying that if this is the configuration, then you have to go to the state Q2 and write it as some other symbol, let us say 1 or 0, and then let us say X, something, if you remember that transition. Okay, let us say X, and you might have to move right or left. Then what will this one do is, our universal Turing machine will see this configuration from this representation of the Turing machine, and it will change the internal state from Q1 to Q2. It will just write Q2, so that it will remember that now we have entered the new state Q2, and along with that it will do whatever modifications are specified on the input in this input, which means it will make that 1 as X, and it is asking you to move right. Therefore you will move right and you will see the next symbol. Then again what will you do? Again you will see that the configuration is you are in state Q2 and now you are looking at the symbol 1. Then what should be done? Then again our universal Turing machine will visit the representation of our Turing machine and see for this configuration what has to be done. Then appropriately it is going to apply the changes. Got it? Therefore, in order to represent in which state we are in at present, we are going to use tape 3, and in order to represent what is the input we are looking at and what has been done to the input, we are going to use tape 2. And in tape 1 the entire mystery lies. The entire Turing machine, some other Turing machine, has to be saved in one tape. How are we going to do that? That is the mystery, isn't it? So to solve that mystery, what we are going to do is, how can we represent this entire some other Turing machine in one tape, right? So what we assume is, without loss of generality, what we assume is that the original Turing machine has set of states Q as Q1, Q2, Q3, Q4, so on, and the tau means the input alphabet as A1, A2, A3, A4, so on, and A1 could be blank, or we could assume any other symbol. So every symbol is represented like this and every state is represented like this. I am not talking about a specific Turing machine which is going to add. In general, it can be applied to any Turing machine. So if you have any general Turing machine, you can represent it in number of states and number of this input symbols, I mean the symbols which are allowed on the tape. Then what we do is, we encode every symbol. So for Q1 the encoding I use 1, and for Q2 the encoding I use is 1 1. For Q3 the encoding I use is 1 1 1. For Q4 the encoding I use is 1 1 1 1. Similarly, for A1 the encoding I use is 1. For A2 the encoding I use is 1 1, and for A3 the encoding I use is 1 1 1. A4 the encoding is like this, so on. I can continue encoding them, right? Now we know that every symbol which is required in these states to represent a state, or every symbol which is required to represent a input, is going to be encoded. There is no problem in using the same encoding for state and then the input, because in transition function we are going to use it. I'll show you how it is going to be easy. Now all the ones are used for encoding, and now I am going to use the symbol 0, this particular symbol, as a separator. So whenever I put a 0, it means that to the left of it there is something else and to the right of it there is something else. Now how to represent a Turing machine is, we have to represent its transition function. Now assume that in the transition function I have something like this, delta of, if you are in state Q1, let me write it here. In this transition function, let us say I have something like this, delta of, if you are in state Q1 and if you are looking at symbol A1, let us say you want to go to, the transition is defined as, you have to go to state Q2 and make it to A2 and move right if this is the symbol there. Then how can you represent this in terms of zeros and ones is simple. See this, Q1 already we represented as 1 1 and then followed by 0, so that we can differentiate it, and then A1 we already represented as 1 and then followed by 0, differentiated, and then Q2 is represented as 1 1 and then write as 0, so that you can differentiate it, and then A2 is 1 1, we already seen it. And now for right and left also we could use some encoding. Let us say for left it is 1 and for right it is 2 ones. Then I am going to write it as 1 1. Then again the next symbol is going to follow, right? So using a string of 1 1, I can represent every transition. So the entire transition function for a Turing machine can be represented as a string of zeros and ones. It has a very important implication which we are going to see later. But for now, understand that every Turing machine can be encoded as a string of zeros and ones. Now these strings of zeros and ones will be kept in this T1. Okay. Then how does this universal Turing machine work? If you want to use a Turing machine as an adder, you design the entire Turing machine, and now we have seen that every Turing machine can be represented as a string of zeros and ones, and now that representation is going to be stored in the tape T1. Therefore, universal Turing machine is going to see the actual Turing machine, which means the program which you have given to it, and it is going to see the input, and then it is going to use this tape T3 in order to simulate what happens if this Turing machine actually runs on this input. So that is how this can be used as a computer. Okay, therefore Turing is right. A Turing machine can be used as a computer, and Turing machine is as powerful as a today's digital computer, right? And one important point here you should remember is, from all this discussion you had to remember one important point. Every Turing machine can be represented as a string of zeros and ones, which means you can take any Turing machine and encode all its states and the input symbol into ones and use 0 as a delimiter, and then you could encode the delta. See that transition function is nothing but a Turing machine, isn't it? So if you could represent the transition function in terms of zeros and ones, it is nothing but we are representing any Turing machine in terms of zeros and ones. Therefore one important point you should remember here, and again we are going to revisit this point, every Turing machine can be represented as a sequence of zeros or ones. Therefore a Turing machine is nothing but a string of zeros or ones. So how can you represent a Turing machine is, if I have sigma equal to 0 comma 1, and if I construct the language sigma star, then Turing machine is nothing but one of the string of this language. But then just be careful that every string of zeros and ones may not be a Turing machine. Okay, I'll just tell you two statements, just write it down. One statement is, every Turing machine can be represented as a string of zeros and ones. That is one statement. And the second statement is, not every string of zeros and ones might be a Turing machine. The reason is, if you take a random string, it may not get converted to a Turing machine. But then if you take a Turing machine, we can convert it. Keep that in mind. Okay. Therefore, the Turing machine is nothing but a string of zeros and ones, right? So that is how we have proven that Turing is actually right, that a Turing machine can be used as a computer. So finally, to wrap it out, I have three tapes, T1, T2, T3. At any point I am going to use T2 and T3 to find out the configuration of the tracing, and then I'll use that configuration and I'll go into T1 to see how the Turing machine behaves in that configuration, and once I get that transition, I'll apply the changes on these two. Got it? That is how our universal Turing machine can simulate any Turing machine on the given input. Therefore Turing is right. Turing is right, right? We have seen that by giving a Turing machine more facilities like more tapes, or by giving it more options like stay option, or by giving it determinism or non-determinism, we have seen that we are not able to extend the power of a Turing machine. Therefore, whatever are the languages accepted by Turing machine, the languages are going to be same. We are not able to extend it by doing any more modifications. But an interesting question is, we are not able to extend the power of a Turing machine. Can we limit the power of a Turing machine by restricting the way in which we are going to use the tape? So the interesting question is, what I want to ask is, by limiting the tape, usage of the tape, can we restrict the power of a Turing machine? That is what I wanted to know. By giving it more tapes and by increasing it, giving it more facilities, we are definitely not able to increase the power of a Turing machine. But then my question is, by restricting the way the tape is used, can we decrease the power of the Turing machine? And the answer is, it turns out to be yes. For example, if I have a Turing machine, and now if I have a tape, and on the tape, if I limit the Turing machine, let us say this is a non-deterministic Turing machine. If I limit the Turing machine to use the tape like a stack, which means it can only push it, using a tape as a stack is simple. So you can say that it is the bottom of the stack, the tape itself, and now once you move here, you should always read the top of the stack only, and then you should write something there. So that is how. So if you limit the non-deterministic Turing machine in such a way that it can use the tape like a stack, then it converts to a PDA, isn't it? If I limit the tape to be used as the stack and given non-determinism, then it will act as a push down automata. And what if I limit the tape not like a stack, but then if I give a Turing machine a tape, and then now I ask it not to use the entire tape, it has to use only a finite amount of tape, which means only this part, it should not use beyond that, then it is nothing but it is a finite automata with a finite amount of memory. Therefore it will boil down to finite automata. Okay, so things you should remember is here, if I have a Turing machine which is non-deterministic Turing machine, the reason is push-down automata can be non-deterministic as well, and we know that non-deterministic push-down automata is more powerful. So if a Turing machine has to act as a non-deterministic push-down automata, at least the finite control should be non-deterministic. Therefore, if a non-deterministic Turing machine is given the tape, but then is given the tape, but then it is restricted to use the tape as a stack, then it is just as good as push-down automata, PD, which is nothing but it is as good as push-down automata, which is nothing but non-deterministic push-down automata. Okay, and now if we restrict a Turing machine, tape of the Turing machine to a finite size, which means we are not going to let it use let us say the finite is fixed, whatever is the size of the input given, we are always supposed to use that finite amount of cells, let us say 10 cells. It is not supposed to use beyond that 10 cells or 20 cells. I'll fix it in the beginning, and the Turing machine should use only those fixed amount of memory, then it is nothing but a kind of finite automata. You remember, finite automata has a capacity to remember only finite memory, which means inside its transitions, whatever is present, that is the memory of the finite automata. Therefore, if I have the Turing machine with the tape as at the restriction that the tape is finite, it is not infinite on both the sides, therefore Turing machine is not supposed to use infinite length tape. If I have that restriction, then the Turing machine will just become a automata, finite automata, right? So these are interesting, isn't it? So we are able to restrict the power of a Turing machine by restricting the way it is going to use a tape. And one interesting modification is, what if I restrict, what if I say to a Turing machine that it can use the tape, but then it can use the tape only in the part on which the input is present. Understand this? So now I am going to restrict a Turing machine in such a way that it can use the tape, but then on the tape it can use only the part in which the input is present. For example, if the input is AABB, then if I restrict the Turing machine in such a way that I'll put these enclosing symbols here and here, and our Turing machine is not supposed to cross these points, and it can use only this space in which the input is present, that will be an interesting modification, and that is called as linear bounded automata. Therefore, a linear bounded automata is nothing but a Turing machine, but then which is restricted. Restricted means it is not supposed to use beyond the input. Therefore, it is supposed to use Turing machine only, but then on the tape it has to use only the part in which input is present. Now what is the difference between this one and the finite memory is, finite means whatever is the size of the input, the Turing machine is supposed to use only a fixed number. It doesn't vary according to the size of the input. But then if I have this linear bounded automata, the Turing machine will get the opportunity to use large memory in case if the input is large, and less memory in case if the input is less. Therefore, for smaller strings, the Turing machine will get the opportunity to use only small amount of memory, the tape, and for bigger strings it will get a opportunity to use big strings. Okay, now it is called linear bounded automata. And now we found out that this linear bounded automata is less powerful than Turing machine. Okay, so understand this. Now we have got a new machine which is not finite automata, which is not push down automata, which is called linear bounded automata. What is linear bounded automata? It is a Turing machine which is modified in such a way that you are not supposed to use anything other than the input. So wherever the input is given, you are supposed to use only that input, not beyond that. Okay, that is called linear bounded automata. And now some important interesting things about linear bounded automata is it is definitely powerful than push down automata. I'll just give you one example which cannot be accepted by push down automata, which will be accepted by linear bounded automata. For example, if I have a power n, b power n, c power n, we clearly know that it cannot be accepted by a push down automata. The reason is we have c power n. A power n, b power n can be accepted by push down automata, remember? And now this cannot be accepted, this can be accepted by linear bounded automata. How? Now the linear bounded automata has the facility to use the memory or the tape on which the input is present, and we are lucky that for this language, in order to accept it, we don't need any extra space. We just see the A, mark it X, see the B, mark it Y, see the C, mark it Z, and again come back and do the same. Therefore we are never crossing the boundaries. Therefore this language can be easily accepted by linear bounded automata without using any extra space other than the input. For example, if the input is AA, BB, CC, and if there are bounds on either sides, then linear bounded automata can simply use only this space and accept it. How? Make it X, make it Y, make it Z, make it X, make it Y, make it Z, over. It need not go beyond it. It need not go beyond the end markers. They are called end markers, right? So I have given you one language which can be accepted by linear bounded automata and which cannot be accepted by push down automata. Therefore we can say that linear bounded automata is more powerful than push down automata. But then it is not the actual proof. I cannot say like that. The reason is, if I have to say that linear bounded automata is powerful than push down automata, then linear bounded automata should accept every language that is accepted by push down automata. I didn't show you that, but then just go with this and remember it that linear bounded automata is more powerful than push down automata, and the proof is going to be very, very difficult. So don't get into the proofs. For now, just understand that linear bounded automata is more powerful. And if you want the proof, I'll just give you a hint of how to prove it. Now already we are having that memory, right? The tape. You just change the tape into a stack, and you will never need more than the size of the input as a stack to solve any problem in push down automata. Okay, I don't think that you will understand it. If you understood it, it is fine. Otherwise, leave it. I'll just repeat it. You can rewind the video and watch it once again. I'll just repeat it. If you understand it, it is fine. I'm saying that a push down automata can solve any problem that it can accept any language that it wants to accept by not pushing more than the size of the input onto the stack. Therefore, you can use the linear bounded automata in such a way that you convert the given tape with the given input into a stack, and already we know that that tape is as big as the input. Therefore the stack is as big as the input. Therefore any problem that can be solved by push down automata can also be solved by linear bounded automata. Anyway, if you didn't understand it, leave it. Okay, so only thing you should keep in mind is linear bounded automata is also a Turing machine with just the restriction that it should not go out of the bounds. That is why it is called linearly bounded. It is linearly bounded to the size of the input. Whatever is the size of the input, you just use that space, don't go beyond it. Okay, and now it is powerful than push down automata, but powerless compared to Turing machine. Therefore, if you compare about the powers of all the machines that we have seen till now, so one thing is finite automata is less powerful than push down automata, and push down automata is less powerful than linear bounded automata, and linear bounded automata is less powerful than Turing machine. Why? Turing machine doesn't have any restriction. And coming to the case of determinism and non-determinism, finite automata is equivalent both the versions, deterministic as well as non-deterministic. It is equivalent. And push down automata is not equivalent coming to deterministic and non-deterministic. Non-deterministic is more powerful than deterministic. And coming to Turing machines, both deterministic and non-deterministic Turing machines are equivalent in power. You please keep noting it down. And coming to linear bounded automata, we don't know. Coming to linear bounded automata, we don't know whether a deterministic linear bounded automata is equivalent in power to non-deterministic linear bounded automata. But whenever I am comparing about the power of linear bounded automata and then push down automata, I am assuming that the linear bounded automata is non-deterministic in nature. Otherwise, I cannot say this. And we don't know what is the power of a deterministic linear bounded automata. We didn't find it out. So just understand that no one right now knows whether linear bounded automata, deterministic and non-deterministic versions are equivalent or not. Again, finite automata is equivalent, deterministic, non-deterministic, note it down, and push-down automata not equivalent, and linear bounded automata undecidable, no one knows whether they are equivalent or not, and Turing machines, they are equivalent. Okay, and when I am talking about the powers, I am talking about taking them as non-deterministic machines in all the cases. In case if I take deterministic linear bounded automata, I might not be able to compare it with push-down automata. So my assumption is, when push-down automata is non-deterministic, let me take a non-deterministic linear bounded automata and compare with push-down automata. Okay, so that is how we can compare all the machines. So we have got now nearly 4 classes of machines, isn't it? Finite automata, push-down automata, linear bounded automata, and Turing machine. And again, each machine can be divided into 2 classes. Therefore, there are totally 8 types of machines: deterministic, non-deterministic, deterministic, non-deterministic. So in everything we have 2 versions, right? So that is how the machines can be classified and the powers can be given. Okay. So I told you that linear bounded automata is more powerful than push-down automata. Therefore, any language that is accepted by PDA will also be accepted by linear bounded automata. And apart from that, there are some other examples, standard examples. These are the standard examples which you might by heart. They didn't ask any such question in the gate, but then they might ask. So to be in safer side, you could by heart this. These are some of the examples of the languages which are accepted by linear bounded automata. Okay, a power n, b power n, c power n. It can be extended. You can put even d power n and anything. Okay, which means using this space you can actually accept it. And a power n factorial and a power n such that n is equal to m square, which means n is a perfect square. And then a power n, n is a prime, a power n, n is not a prime, ww. It is an interesting language. Ww means there has to be a string followed by the same string. In order to accept this, what our Turing machine should do is, it should be able to find out the center. I am not going to give you the proof, but then I will just give you a hint about how to find out the center. What you could do is, mark the first, if the input is small a small b, then you change it to capital A capital B. If the input is small a small b like this, you change it to capital A capital B in order to mark it. So how to find out the center is, if the input is given as a b, now you first change the left side, this one to a, and go to the right end, change it to b, this one to a and this one to a, this one to b and this one to a. So whenever you come across this, you can say that this is the center. So how to remember the center is simple. So you keep on marking the left side, left and right end, left and right end like this, and whenever these two ends meet, that is the center. And once you have identified the center, then just see if from the center, if two, you can start matching like this. You can mark the center and you can start it. Proof is not important, I just given it for the sake of explanation, but then nothing is going to be asked like this in gate, so proof is not important. Maybe if you can by heart these examples, it is better. And other is w power n. So here also you should find out what is the size of the n, right? What is the size of the w, then only you can see how to compare each one. And again w power r. So you can extend these languages, but these are the standard models. These are the languages which are accepted by LBA, apart from the languages which are already accepted by PDA. Anything accepted by push-down automata can be accepted by linear bounded automata. Just remember these examples. Okay. Now, like the regular languages and context-free languages, is there any name for the languages accepted by Turing machine? That is the question. Which means the set of all languages accepted by Turing machine, what do we call them? So they have named them as recursively enumerable languages. Recursively enumerable languages, which means if for a language there is a Turing machine, or if a language is accepted by a Turing machine, then that language can be called as recursively enumerable languages. But just keep in mind that whenever I am discussing about all this, I am going to say that Turing machine is powerful than push-down automata. Therefore, context-free languages are a subclass of recursively enumerable languages, which means any language which is accepted by a push-down automata can also be accepted by a Turing machine. Therefore, by definition, context-free grammars or context-free languages should be present inside the recursively enumerable languages. But Turing machines doesn't have the power to accept epsilon, which means null string will not be accepted by Turing machines, but then null is present in push-down automata, which means they are present in context-free grammars, context-free languages. So whenever I say that the context-free languages are subset of recursively enumerable languages, just keep in mind that I am not considering the languages having epsilon. So epsilon doesn't make a lot of difference. So you can remove epsilon from all the languages, and then whatever I am going to say is going to be valid. So just for the sake of epsilon, I don't want to miss out this comparison. That is why we are not talking about epsilon. From now on, my assumption is that any language that I am going to talk about is not going to contain epsilon. Okay, just keep that in mind. Now, any language that is accepted by Turing machine is called recursively enumerable language. That is what I am saying. And if there is a Turing machine, what does it mean? Okay, first of all, what is a language? First we are going to define sigma, and then we are going to define sigma star. Sigma star is nothing but set of all strings possible, and a language is nothing but subset of sigma star, which means a language is this. Now whenever I say that there is a Turing machine for a language, it means that to a Turing machine, if I give any string from this language, it is going to say yes, the string is present in the language. If you have such a machine, then it is called as recursively enumerable language. But then the problem with a Turing machine is it may not halt. It may sometimes fall in infinite loop. Okay, so you please write down whatever I am saying. Whatever I speak, you just write it down so that later it will be easy for you to understand. And now, if a string is not in the language, which means if the string is not present in the language, and if I give such a string to the Turing machine, then the Turing machine may say no, which means it may halt and say no, which means it may halt in a non-final state, or sometimes it may fall in infinite loop. This is the problem with Turing machine. So understand this. For a language, if there is a Turing machine which is accepting the language, then it is called recursively enumerable language. But the problem with Turing machine is, if a string is present in the language and if I give it that string, it will stop and say yes, the string is present in the language. But if the string is not present in the language, if I give it such a string, it may say no. Sometimes if you are lucky, it will halt and say no, and sometimes it will fall in infinite loop. It will say that I am still processing, you please wait. Now you have given a string to a Turing machine. It is saying that I am still processing, you please wait. You don't know how much longer to wait. Maybe if you wait for some more time, it is like this. Maybe you might have seen this problem when you are calling this customer support will be there. I think Airtel or something. Airtel, whenever you call them to speak to a customer service representative, you will be waiting in the queue, and they will say that please wait, we are going to attend your call shortly. Now let us say you have waited for half an hour, and now you don't know whether to disconnect it or not. The reason is they are asking you to wait, and you don't know what is your number. Maybe if you wait for one more minute, you might get the call, or if you disconnect now, who knows, maybe the call is it might take one more hour, and disconnecting it is the right choice. So we never know that. Similarly here also, you understood the correlation. I am saying that you call some customer service representative and they are not answering your call, they are putting your call on hold. Now how long should you wait? They are asking you to wait. but you don't know how long is it going to take. It might take forever. They might answer in 1 minute, they might answer in 1 hour, or they might never answer and you have to keep on waiting throughout your life. So what is that you are going to do? If you cut the call, who knows, maybe in 1 hour or maybe in 1 second they might attend the call, and you are just waited so long and you are just stopped it there. Similarly, whenever Turing machine falls in infinite loop, the problem is we don't know whether to wait or whether to stop the Turing machine. If you wait in a hope that answer might be just in the next step, then you might be wrong and you might keep on waiting. But if you stop it, sometimes what happens is answer might be actually in the next step and you have stopped it. So you don't know that. That is the problem with the Turing machine. Understand it? Now, I don't want such a dilemma. What I want is, I want a Turing machine which should definitely say yes or no. It should never fall in an infinite loop, which means it should take some time, any time, I don't care, but then it should say yes, it is present, or no, it is not present. Which means if I restrict a Turing machine in such a way that I am going to ask the Turing machine more specifically, say yes or no, don't please fall in infinite loop. If I ask it in such a way that, then what happens? See this? Now if this is the sigma star, set of all strings possible, and if it is your language L, and now there is a Turing machine. Now this Turing machine is designed in such a way that if any string is given from the language, if the string is present in the language, it will say yes, this string is present in the language. If the string is not present in the language, if it is given to the Turing machine, if it says no, and it is not going to fall in infinite loop. If such is the characteristic of the Turing machine, then this is called as halting Turing machine. Halting Turing machine. Okay, so halting Turing machine means a Turing machine which always halts wherever or whatever the input string is. Either you give the input from the language or you give the string input outside the language, it is always going to halt. If the string is present in the language, it is going to halt in the final state, and you can say that yes, the string is present in the language. If the string is not in the language, it is going to halt in a non-final state, and you can say that no, the string is not present in the language. Okay, so understand the difference. Now recursively enumerable language means if there is a Turing machine, I don't care whether it is halting machine or non-halting machine, if there is a Turing machine for a language, then I can say that the language is recursively enumerable. Then there is a subclass of languages where the Turing machine always halts. If the Turing machine always halts, it is called halting Turing machine. If for a language, if there is a halting Turing machine, then such language is called recursive language. Recursive language. Okay, so try to understand the difference. If there is a Turing machine, then the language is recursively enumerable. If there is a Turing machine which always halts, if I add that one more statement which always halts, then that language is called recursively enumerable. Sorry, recursive language. Therefore, you can think of the languages like this. If this is all set of languages which are recursively enumerable, which means these are all the set of languages for which there is a Turing machine definitely, then the set of all languages which are recursive will fall here. Regular languages are different and these are different. Recursively enumerable means there is a Turing machine, and recursive language means there is a Turing machine which halts. Therefore, by definition, every recursive language is a recursively enumerable language. Why? Because recursive language, enumerable language says that if there is a Turing machine, I don't care about anything, it is a recursive enumerable language. And now recursive language says that yes, there is a Turing machine which halts, but then it doesn't care whether it is halting or not. Therefore, every recursive language is recursively enumerable language, but then the reverse is not true, which means I cannot give you if a language is recursively enumerable, it need not be recursive language. The reason is the Turing machine, that particular Turing machine might not halt. Okay, so depending on this halting, we have got two types of languages. One is called recursively enumerable and other is called recursive languages. And we have already seen that there is one more language which is linear bounded automata, isn't it? Now the language accepted by linear bounded automata is called context sensitive language. context sensitive language, and context sensitive language falls here. Therefore linear bounded automata is a halting Turing machine. Okay, so now I have told you that there are three types of languages. One is, if there is a Turing machine, that language is called recursively enumerable. Second is, if the Turing machine halts, that language is called recursive language. And third thing is, if the Turing machine halts as well as it is going to use only a part of the tape on which the input is present, then that is called context sensitive language. Okay, so if you look at the entire languages, now I have added three more languages. You already know about regular languages and you already know about context free languages. Now I have added three more languages. Now what I will do is, I will show you the relationship between all these languages without any confusion. So if there is any confusion, just revise it one more time. You just play the video once again and just go through this. What I mean to say is, Turing, the biggest language power set is this recursively enumerable, inside that recursive, inside that context sensitive. Anyway, I'll just show you now with a big diagram about what are the machines and then what are the languages, corresponding languages. Okay, now let's see what are all the types of machines we have seen, and what are the languages associated with them, and what are the grammars associated with them. So just follow the way I am going to construct the diagram. The way I construct it is going to answer lots of questions, so just follow it closely. See this. Now let us say this is the set of all Turing machines. Then the languages accepted by set of all Turing machines are called, let me call it as recursively enumerable languages. So what does it mean? If a language is going to have a Turing machine, I don't want to know anything about the Turing machine, what type of Turing machine it is, deterministic, non-deterministic, halting, non-halting, nothing. If it is having a Turing machine, then that language is called recursively enumerable language. Then the subset of machines, Turing machines, which will always halt, the subset of Turing machines which will always halt, they are called halting Turing machines. Now the languages accepted by these halting Turing machines are nothing but subset of recursively enumerable languages, and these languages I call them as recursive languages. Recursive languages. So Turing machines correspond to recursively enumerable languages, and halting Turing machines correspond to recursive languages. Okay, and now this subset of the machines, these Turing machines, which will use only the stack or the tape which is limited to the size of the input, that is called linear bounded automata. And the languages that are accepted by this linear bounded automata are called context sensitive languages. Context sensitive languages. Okay, and whatever language is accepted by linear bounded automata is also called as context sensitive language, which will be subset of it. Right, and now the subset of the language, these machines, one of the subset is non-deterministic push down automata, or let us say only push down automata. Why to put one more, or okay, let's put non-deterministic push down automata into picture here. So our space is not going to be enough. Let's see, non-deterministic push down automata, and these languages are called set of all context free languages. Right, and now a subset of this non-deterministic push down automata is nothing but a deterministic push down automata, and the languages accepted by this deterministic push down automata are nothing but deterministic context free languages. Deterministic context free languages. Deterministic context free languages are actually a subset of context free languages. Okay, and now finally the machine which is subset of this deterministic context-free language push down automata is finite automata, and the languages accepted by that machine is regular languages. Okay, so understand this. Now the way I have constructed the diagram will explain you some few things. Now every recursive language is recursively enumerable language. The reason is, if there is a Turing machine which halts, that is enough to say that there is a Turing machine. Therefore, by definition, any language which is having a Turing machine is nothing but recursively enumerable. Now every context sensitive language is recursively enumerable. The reason is, context sensitive language is nothing but a Turing machine. It is a language accepted by a Turing machine which is bounded to use only the input part. So since there is a Turing machine, it is also recursively enumerable, and moreover this context that linearly bounded automata is supposed to halt. Therefore it is a subset of recursive languages. And next thing is context free language. Now I told you that we can modify the Turing machine in such a way that the Turing machine can be used, or the Turing machine can be modified in such a way that the tape can be used as a stack. Now when we are using the tape as a stack, it is nothing but the push down automata. Therefore push down automata is nothing but a Turing machine which is going to use the tape as a stack. Therefore every context free language is also recursively enumerable language. And moreover, regular language is nothing but a finite automata. The language accepted by finite automata, and finite automata is nothing but a Turing machine in which the tape is limited to the finite amount of space. So if I do such a modification to a Turing machine, since that is a Turing machine, it is recursively enumerable. So you can answer all the questions. So questions will be like this: every regular language is context free, and every context free is context sensitive. Every context sensitive is recursive. Every recursive is recursively enumerable. That is the relationship between the languages and the machines. Now let's see the relationship between the machines, languages and grammars. We have already seen some few grammars. So one type of grammar which we have already examined is regular grammar. So regular grammar are the grammars which will generate the regular languages, and next one is context free languages. So for context free languages, we already have the grammar. Don't distinguish between the deterministic and non-deterministic context free languages. You can say that context free grammars, CFG, are the grammars which are associated with context free languages. And next one is context sensitive languages. Let me check where it is. Next one is context sensitive languages. Therefore for context sensitive languages, the corresponding grammar is context sensitive grammar. And next one is recursively enumerable languages. For the recursively enumerable languages, the corresponding grammar is unrestricted grammar. Unrestricted grammar. We have basically these 4 types of grammars, and you need not worry about recursive languages or deterministic and non-deterministic context free languages. But then basically we have these 4 types of grammars. It is also called as type 3 grammar, type 2 grammar, type 1 grammar and type 0 grammar. Now we shall see more about this each of these languages and more about each of the grammars. Okay, so you can now understand what is the relationship between various machines, and then what is the relationship between machines and the languages, and languages and the grammars, and therefore what is the relationship between the machines and the grammars. Okay, so we have got all these languages now, all these machines. Now let's see the properties of them. So the way I want to examine it is, I'll come with the Turing machines and then halting and then linear bound automata. And however, you already know about finite automata, push down automata and context free languages and regular languages, context free grammars and regular grammars. Only thing you are supposed to know is what is Turing machine and then what is the language associated and what is the grammar. So let's talk about the grammars associated with Turing machines and linear bounded automata. Okay. Now look at this type of grammar which is called unrestricted grammar. So I told you that the languages accepted by Turing machine are called recursively enumerable languages, and the grammars which will generate these languages are called unrestricted grammars. Okay, so just keep that in mind. The languages corresponding to Turing machine are recursively enumerable, and the grammars corresponding to this recursively enumerable are unrestricted. Maybe write it down. Languages corresponding to Turing machines are called recursively enumerable languages, and the grammars associated with this recursively enumerable languages are called unrestricted grammars. Okay, this is the relation. Now watch this. A grammar is called unrestricted grammar if all the productions are of form U derives V, which means if I have all the productions like this, then it is called unrestricted grammar, where U is in V union T plus. So what does it mean? The left hand side can contain any number of variables as well as terminals, but only restriction is that left hand side should not contain any epsilon. The reason is there is plus, it is not star. Just keep that in mind. The left hand side can contain anything, only restriction is that it should not contain any epsilon, which means the null string should not derive any other string. That is the meaning of it. Except other than that, you can have any number of symbols on the left hand side. You can have only terminals, or you can have only variables, or you can have a combination of variables and terminals. Anything is fine, but either, and they can come in any order. That is okay. Nothing is, no, there is nothing wrong, but only thing is you just see that there is no epsilon in the left hand side, and the right hand side is completely unrestricted. So you can have anything including epsilon in the right hand side. Okay, so if you have such a grammar, it is called unrestricted grammar, right? Now let's look at this one. What language does the following unrestricted grammar derive? So they have given some unrestricted grammar. Okay, first of all, is this unrestricted grammar? Just check this. Left hand side could be anything, any combination of variables and terminals, and right hand side could also be any combination of variables and terminals, but the left hand side has to be a non-null, as it is unrestricted grammar. And one more thing, unrestricted grammar can derive epsilon, which means empty string, but I told you that according to the definition of Turing machine, it doesn't have a capacity to accept epsilon, because if there is nothing, we cannot define nothing on the tape. There is a symbol called as B. Therefore Turing machine is not configured in order to accept a empty language. But then here I am showing you that this unrestricted grammar is going to derive all the languages accepted by the Turing machine, which means it is able to accept even epsilon. It is able to generate even epsilon. But then our Turing machine does not have epsilon. So just keep in mind that I am just talking about the languages in which there is no epsilon. Completely throughout the discussion of this topic, keep in mind that I am talking about the languages which are not having epsilon. Okay. Now let's see this one. They are given you this grammar, and they are asking you what is this one deriving. So just look at this and try to understand it. So by reading the grammar, you should be able to understand it. In case if you don't understand the meaning of it by reading the grammar, the next step is try to derive all these strings, and then you see the pattern and you identify it. Let's try to read it and understand it if you could. Okay. First one is S derives S1 followed by capital B, and S1 is A S1B. So you might have seen such a kind of grammar previously in context free grammars. Now what does S1 derive? A power n, B power n, isn't it? Now what is capital B doing? It is taking 1B and it is generating 3 B's, which means it is simply taking 1B and it is replacing with 3 B's. Next time again it will take 1B and replace with 3 B's. So it is actually increasing the B's with a common ratio of 2, which means that in AP the common difference is 2. It is taking 1B and every time it is incrementing it by 2 B's. So initially if there is 1B, then later it will be 3, and later it will be 5, and later it will be 7. So it is going to increase like that, and or B is going to simply generate null, which means B can terminate at any point. Initially it will take 1B, it will keep on expanding it by incrementing 2, 2, 2, 2 like that, or it can stop at any point. And AS1B is reducing to AA, which means S1 is taking 1A, 1B and combining AB to AA. So S1 is reducing the number of B's or converting one AB into AA. So if you could understand this, it is simple. S1 is nothing but A power n, B power n is generated by S power S1, and at last it is going to dissolve one AB into AA. Therefore, S1 is going to generate A power n plus 1 followed by B power n. So finally this S1 is able to generate A power n plus 1. Why plus 1? The reason is it is going to take a AB and it is going to convert it into AA. Therefore at the last step, even though initially A power n, B power n is generated, at the last what happens is number of A's are going to be increased by 1 and number of B's are going to be decreased by 1. And later what is B is trying to do is B can add any number of B's. So B can take 1B from this and then it will keep on adding 2 more B's. Therefore B power 3K, isn't it? So if you didn't understand this, the explanation, what you could do is you can just look at all these strings generated by this and you can guess it. Now one derivation is giving us AA, other derivation is giving us AA followed by B's. So if you look at this pattern, you could write like that: L equal to A power n plus 1, B power n plus k. A power n plus 1 and B power n plus k, where n is greater than or equal to 1. So you could work it out. What you do is you generate many strings from this language and then you can check that this equation is going to be followed by all the strings generated. You can just check it. So in the options, what you do is, if all the options are given, you just generate all the strings and then take every string and see that it is following that rule or not, right? Okay. A grammar is said to be context sensitive if all the productions are of form x derives y, where x comma y belongs to v union t plus and mod x is less than or equal to mod y, which means a grammar is said to be context sensitive if you have all the productions of form like this and x and y, they both belong to v union t plus. So x and y can be any combination of variables and terminals, but only restriction is either in the left hand side or in the right hand side we are not going to allow epsilon at all, because both of them are going to belong to v union t plus. That is the main difference between unrestricted grammars and context sensitive grammars. In unrestricted grammars, what we had is in the right hand side we are allowing epsilon, but here we are never allowing epsilon. And now look at this restriction. The left hand side, the length of the left hand side string is always less than or equal to length of the right hand side string, which means we are always going to expand the derivation. So whenever we take the left hand side and when we substitute with the right hand side in the process of derivation, the string length will always be in the increasing order, which means at every step of derivation we see that the length of the derivation, the length of the string either remains same or it is going to increase. Are you understanding it? See this, the left hand side length is always less than or equal to right hand side length, which means if you replace a string x with a string y in the derivation procedure, what happens is in the process of derivation, whenever you replace it, either the string length is going to be constant, is not going to change in case when string lengths are same, or the resulting string length is going to be increased in case if the string length of the right hand side is more. So what does it mean? Always the grammar is non-contracting, or non-contracting means it will never contract, it will always expand or it will remain same. It is called non-contracting. Okay. And then I think it is obvious to see why it is why it is called context sensitive. The reason why it is called context sensitive is, if I have a production in context free grammar, it is A. It is context free in the sense wherever you see capital A, you can replace it with small a. This grammar is called context free, remember? And capital A derives small a is context free because wherever you see capital A, you can replace with small a without worrying about the context in which capital A has occurred. But then in this one, if I have something like this, A B derives A B, then it is not actually replacing capital A with small a, which means you cannot remove this production and you cannot add this production directly, even though it is looking obvious that capital A is going to be replaced by small a by this expansion. It is not true. Actually, capital A is going to be replaced with small a only in the condition when capital A occurs when its left hand side is a, small a, and its right hand side is small b. It is nothing but context sensitive. So we are going to do this replacement only in the context where capital A has occurred between a small a and small b. Then only we are going to replace capital A with small a. So we are not, it is not straightforward, it is not context free. That is why it is called context sensitive. So the grammar is called context sensitive because we are going to apply many of the rules looking at the context in which a variable is occurring. It is not that every time there is capital A we are going to do it context free. Got it? That is why it is called context sensitive. We shall see an example of how to use the context sensitive grammars, or how they look like, and how we can do the derivation. Okay, we shall see example. Let's look at an example of context sensitive grammar. But before going ahead, I'll just tell you a few points about this unrestricted and context sensitive grammars. First thing is, these two are very difficult to write. It is not very easy like we have practiced with context free grammars. These are very difficult to design, and there are only a handful of examples available. There are not lot of examples available, and one good thing is, till now they have not asked any question about these grammars in GATE. Till now no question has been asked, and maybe to be on the safer side, I'm just explaining you how they work. But then I don't think that if they ask you such a question in exam, GATE exam, to design the grammar, it is very difficult. Maybe they might ask you a question like this: given a context sensitive grammar, what is the language generated by this? They'll ask you such kind of questions. So just know, or just understand how to derive a string. I think that you already know it, right? Okay, now let's look at this example. What is the grammar generated by the following context sensitive language? Okay, before going ahead, one more thing. In context sensitive grammars, I told you that the right hand side and left hand side can be anything but not epsilon. Therefore, by definition, context sensitive grammars does not generate any epsilon. Therefore, context sensitive languages does not contain epsilon. But then in the diagram, I told you that context sensitive languages are actually superset of pushed on these context free languages. There also the assumption is epsilon is not included. Okay, now watch this. This is the grammar given. They are asking you what is the language generated by this grammar. First of all, if they have given you the language and then if they have asked you to come up with the grammar, it would be really difficult. One good thing is they are already giving you the grammar and then they are asking you what is the language accepted, because it is easier to do that way. Okay, and don't worry, in GATE they will not ask you this. And so how to do it is, just try to derive a string, then you will understand what is the language generated by this. Actually, the language generated by this is a power n, b power n, c power n, such that n is greater than or equal to 1. A power n, b power n, c power n, n is greater than or equal to 1. To see this, let's see an example with that. So I have just written down the derivation. So what I did is, initially I started out with this production, and then I started expanding like this step by step. But then anyway, let's see this derivation and I'll explain you how the grammar works. So first thing is, I derived ABC. Either you could derive ABC directly, or you could use small a, capital A, BC. If you have used ABC, your derivation will end there, which means you are going to generate a power 1, b power 1, c power 1, which is in the language. So that is the smallest string. In case if you are using this, it means that you want to derive a bigger string compared to this. And why is it bigger? The reason is our grammar is non-contracting. So you are always going to expand the string length. So whenever you are using this, definitely we assume that if you go and replace capital A with something, either the string length is going to be 4 or it is going to be greater than or equal to 4. It will never shrink. So definitely I am going to increase the string length by using this. So I have taken this. Then how A is working is, A will start at the left end, which means after small a's, and then it will travel to the right end, which means it will travel till it hits the C, and there it will generate one extra BC and convert it into capital B. Okay, it is very difficult to understand, just try to understand it. What capital A will do is, A will start at the left end after S, and then it will just travel to the right end till C's are hit, and whenever it sees the first C, it will generate one extra BC, and again it will start traveling to the left side. as capital B. So see this, A has started here and now A will shift there, A will move here, and whenever it has hit small c, it will generate one extra BC and convert itself to B. That is what A is doing. So see this, now this move, this production is going to help capital A to traverse over the B's. So it will be at the, see, if there are all A's here and capital A will be here and all B's will be here and C's will be here, then this production will effectively help A to cross over the B's. That is what that production will do. Got it? So see this, A, again let's see here, see, A is starting at the leftmost and it will gradually move until it hits the C. See, A will be moving here and then A will be moving here, A will be moving here, and now once it has hit the C, it is going to generate one extra BC and convert itself to capital B. That is what this one is doing. So this production is going to help A to traverse over B, and this production is whenever A has hit C, which means it has seen C, then it is going to produce one extra BC. C is going to remain there, one extra BC is produced and A is getting converted to B. Got it? And what is the purpose of B is, B will start from this end, right end, and it will keep on moving left, and whenever it hits A, it is going to generate one extra A. So effectively A is going to generate BCs and capital B is going to generate one extra A. So BC will be generated by A and B will be generated by A. For example, you start with A, B, C. Now B will go to the right end and here it will generate BC, which means A, B, B, C, and now again B will start here, it will come to the left end, it will generate A. So balancing out, A's responsibility is to go to the right end and generate a BC, and B's responsibility is to come to the left end and generate a so that everything will be balanced out. 1 BC, 1 A, 1 BC, 1 A, 1 BC, 1 A, like that. Okay. Now just see this. What B is trying to do is, B will start at this point and it will move left, move left, move left. For moving left, it is going to use this production. If BB is there, it is going to write it as capital B small b, which is nothing but moving left. And once it has moved left, it is going to hit this end and is going to generate one extra A. So B is going to generate one extra A, or in case if you want one extra ABC, then you go with this. If you don't want to stop this procedure, already one extra A is generated, along with that you generate capital A also. Now what will capital A do? It will go to the right end and generate BC. Now let's see the entire procedure. Now A will come to the right end and it will generate a BC. BC is generated. Now B will go to the left end and it will generate a A. Now A will go to the right end here, and it will generate a BC. Now B will go to the left end here, and it will generate a A. Like that it will work. So A and B are actually messengers. A will go to the right end, B will go to the left end, right and left end. Like that it is going to work. It is very complex to understand, so I hope that you understood it. But then in exam they are not going to ask you to design such a grammar. It is going to take a lot of time, a lot of time. Maybe you could just try how difficult it is, just to see how difficult it is. Maybe you could just try deriving a grammar for A power n, B power n, C power n. So what should you be doing? Generate AB. See, I'll just tell you the hint. I'll just give you the hint. I'm not going to do it. In case if I have time at the end, I'll do it. But then I'm just giving you the hint. Just see how to generate it. If I have A power n, B power n, C power n, D power n, now you have to go till this point and generate CD, and go till this point and generate AB. Go till this point, generate CD, go till this point and generate AB. It has to continuously happen. Okay. It is going to be difficult. Let me warn you, it is going to be difficult, but it will be fun to try it out. You please try it out. Okay. Fine. Now let's say we have the language A power n, B power m, C power n, D power m, such that n comma m greater than or equal to 1. For this language, I want to construct a context sensitive grammar. So first of all, it is not going to be asked in GATE. Okay, don't worry about it. So don't worry about context sensitive languages at all. I don't think that they will ask you in the GATE. But then it is to be in the safer side, I'm just teaching you. So it is not very difficult, as it is difficult to design it, but then not too difficult. Once I explain it, it will be very easy. So don't get worried about it. So let's just see how to design it. A power n, B power n, C power n, D power n such that n comma m greater than or equal to 1. Definitely this language is not context free. The reason is, if you try to design a push down automata, if you push A and push B, and if you want to compare C against A's, by that time on the top of the stack there will be B's. They will not let you compare C and A's, right? Therefore it is not possible for you to construct a push down automata for this language. That we already know, it is not possible. Then the other alternative, if push down automata is not possible, then the next level is context sensitive languages. Now we have already seen for this language A power n, B power n, C power n such that n is greater than or equal to 1. For this language we have seen the context sensitive grammar. How does this context sensitive grammar, how did it work is, it started here and it slowly moved right, A slowly moved right and generated a BC, and again B slowly moved left and generated A. Like that we use two messengers. A is moving right and generated BC, and B is moving left and generated A. Similarly we can use the same ideas and we can do this question. Okay, so this is entirely the one grammar only. Even though I have written some lines like this, it is completely the grammar. See how big it is. So don't worry about it. It can be done easily only. But then the lines, I have drawn these lines like this so that I want to separate the phases. I want to show you, or I want to explain you what this collectively these productions are trying to do, so that explanation will be easy. So I want to generate A power n, B power m, C power n, D power m. Now these four productions, they are not two, there are four productions. All these four productions combinedly, they want to give the effect, or they want to produce this. They want to produce A power n capital B, C power n capital D. So this is what they wanted to produce. So just see this. If you just want to produce 1A, 1C and BD, you can take this. Otherwise, if you want to produce any number of A's and C's, A power n, C power n, then you can take this production, and then in place of A you can keep on using this, so that A power n, B power n will be generated, and if you want to stop it, you stop it with this. Therefore if you want anything greater than 1, n is greater than 1, then you can use this production followed by these two productions. Anyway, by using all these four productions, finally what could you derive is A power n capital B, C power n, D power n, just like that context free grammar. Okay, if you want to see this, just see this how it is going to happen. If you want to generate directly A, B, C, D, done. If you want to generate A square B, C square D, then what you could do is A, C, D, and now in place of this A you could put A, C, C, D. Now it is nothing but B. In place of this A you could put this, then it is nothing but A square capital B, C square capital D. Therefore using those four productions, what you could generate is A power n capital B, C power n capital D. Now what is the purpose of this B is, B has to go to the right and generate a D and then get changed to some other messenger, let us say E, and now E has to come left and generate a B. Okay, so B has to go to the right and generate a D, and it will convert itself to some other variable, and that variable has to come left and generate a B. So we are going to use D as the end marker, which means B will keep on, capital B will keep on moving right until it meets the end, and when it meets the end it is going to drop a D there, and again it has to come back and drop a B here, because both B's and D's have to be matched. So the same way how we designed A power n, B power n, C power n, here also we are going to do the same kind of traveling and then creating, traveling and creating. So what is that we are going to create here? B has to travel right and then create a D, and then convert itself to some other variable, and again we have to come left and then create a b. Okay, so for that reason what we are going to use is, if b has to travel right, see this production, if b has to travel right, it has to move over c's and b's. Why is it required is, at some point in the derivation you might get a string like this, aa and then bb and then cc and then dd you have, and you will have d here and you will have b here in some point of derivation. Okay, then what should b do is, b should jump over all the b's, capital B, and then it should jump over all the d's, all the c's, and then finally it should meet the d. Okay, so these two productions will help b in traversing or jumping over c's and jumping over d, isn't it? See this, it is nothing but b is jumping this side, that is why b has come here. B is jumping this side, that is why b has come here. Therefore what is happening, b will jump all the b's and then b will be here, and b will jump all the c's, and finally b will meet d. Then what should it do? Whenever it meets d, it is supposed to generate one extra d. Okay, it will generate one extra d, and then if it generates one extra d here, it has to again go there and generate one extra b. Therefore it is going to convert itself to e. So see this, what is happening is, whenever b meets d, which means b has reached the end of c's, therefore that is the point where it could generate a d. Then it could generate one extra d and then convert itself into e. Why? Because once it converts itself into e, then e can come to the left and generate a b. It is not just enough that you generate the d there, you have to even generate b's. Why? B's and d's have to be matched. That is why what happens is, a will keep on b will keep on going here and it will go there, and finally it will generate a d, one extra d, and it will become e. Now what should e do? E should keep on coming left, and once it meets a, it should generate one extra b. Then only d's and b's will be matched. Then what it should do is, e is supposed to jump over c's and b's. Therefore look at this, this move will help e in jumping over c. So it is going to jump like this, that is why e is here, right? E is coming, and again it is going to jump here, that is why e is here. Therefore e is going to jump over all the c's and all the b's, and finally e will go and meet the first a. Whenever it has reached the first a, it will understand that that is the point at which it has to generate a b. Therefore whenever it has reached the first a, then it is going to convert it into b and end the procedure, which means it can stop here and convert into a b. But the problem is, using this, if I kill b here, if I kill d here and if I kill e here, the procedure is going to end. But sometimes, see, you can generate any number of a's and any number of c's using the first four productions, that is fine. But then if I use only till there, that point, we are generating only one d and one b, isn't it? Only this will be generated. If you want to continue this procedure and generate many number of b's and d's, our d should not die here and our e should not die here, and the procedure should be alive. That is why what you could do is, initially when the b has met d, it need not kill d. Let the d be there, generate one extra small d, this n delimiter d be there, and generate one extra small d, and now you convert yourself into f. Now what is the purpose of f? Go to the left and generate one extra a, but then again reproduce b, so that this entire procedure will be alive, isn't it? That is why f will jump all the c's and f will jump all the e's, and whenever it meets a, it will generate one extra b, and it will even reproduce capital B, so that capital B will again go and meet d and produce a d, and again b will meet a and b will convert itself to f and come back and meet small a and produce a b. So this entire method is used in order to generate any number of b's and d's. So initially these four productions are going to generate equal number of a's and c's, and then this procedure is going to generate any number of b's and d's. In case if you want only one b and d, you go with this, or in case if you want to kill this procedure at any point, you can go with this. Got it? That is how context sensitive grammar can be generated for this. It is not asked in GATE. Maybe if they want to ask something about it, they will just give you a blank and they will ask you to fill it up. It is not very easy to understand or answer it, but let's be in the safer side. Since you have already learnt it, better you just write it down, and before the exam you could revise it once. Okay, this is about the context sensitive grammar. This is a very important theorem. I'll just read out the theorem, and maybe you please write it down, and if possible by heart it. Anyway, I'm going to give you the proof, but just you can write it down. See this: if a language L and its complement L complement are both recursively enumerable, then both languages are recursive. I don't think that you'll understand anything now. I'm just reading it out so that you'll write it down, then I'll talk about it. And next one is, if L is recursive, then L complement is also recursive, and consequently both are recursively enumerable. Okay, so what to understand from this given explanation is, so before you understand anything, let me talk about the difference between recursively enumerable and recursive languages. According to the definition of recursively enumerable, I said that if for a language there is a Turing machine exists, then it is recursively enumerable. And when I was talking about recursive languages, I told that if for a language, if a Turing machine exists which always halts, then that language is recursive. So the main difference between recursively enumerable and recursive languages, the Turing machine for recursive languages always halts, and the Turing machine for a recursively enumerable language may or may not halt. So see this, the main difference is, if a language is recursively enumerable, then it will have Turing machine, right? And now to this Turing machine, if I give a string W, then it might halt and say yes, the language is the string is in the language, in case if the string really belongs to the language. Okay, or it may say no, or it may fall in infinite loop. This is the problem. So recursively enumerable languages have the problem that given a string, the Turing machine may say yes, will definitely say yes if the string belongs to the language, and what it will do is it will say no, or sometimes it will fall in infinite loop if in case if the string does not belong to the language. And what is the recursive language is? Recursive language means it will have a Turing machine, and given a string to the Turing machine, it will say yes, this string is present, or no, this string is not present in the language. In case here string does not belongs to the language, then it will say no or infinity, and here if the string belongs to the language, it will say yes, and if the string does not belong to the language, it will say no, straightforward, right? And you need not wait. The problem here is you don't know how long to wait. It might be the case that the Turing machine really needs extra time to compute, and it is really doing some computation, and therefore you might have to wait in that case. Or it might be the case that it has entered an infinite loop, and there is no way you know that you are in the infinite loop. Let us say you are watching a Turing machine, you are sitting and watching a Turing machine, it is doing some computation. Now you don't know whether to switch it off or not, because it is still computing, it is not saying anything. It might be the case that it needs more time really, or it might be the case that it might have entered the infinite loop. Therefore we cannot say anything about that. So the main difference between recursively enumerable languages and recursive languages, Turing machine may fall in infinite loop in case of recursive enumerable languages sometimes, whenever this given string does not belong to the language. And in case of recursive languages, the Turing machine does not fall in infinite loop. Whatever it is, it will give you a straightforward answer. Therefore you could wait until it halts. Here the Turing machine always halts, here the Turing machine does not halt. Okay, now so what is the main difference is, there is something called as membership algorithm. Membership algorithm is given a string and a language. Our question is whether this string belongs to the language. Tell me yes or no. If you can answer that using an algorithm, then that is called membership algorithm. Here membership algorithm is not possible. The reason is, if you give it a string and ask it whether it is present in the language or not, it may sometimes say yes, and it might never say an answer. Therefore you are not going to get a no all the time, right? Therefore there is no membership algorithm for recursively enumerable languages. Write it somewhere. There is no membership algorithm for recursively enumerable languages. But coming to recursive languages, given a string and you ask it the question that whether the string belongs to the language or not, that is called membership question. And for that question, definitely it will answer with yes or no. Why? Because Turing machine is always going to halt. Therefore, for recursive languages, membership algorithm exists. Membership algorithm exists. This is the main difference. Understand this? For recursively enumerable languages, no membership algorithm exists, but for recursive languages, membership algorithm exists, right? So, given a Turing machine, right, that may or may not halt, and if we just say that the language is having a Turing machine and we didn't say anything about whether it halts or not, then it is nothing but a recursively enumerable language. If I say that the language is having a Turing machine which always halts, then it is nothing but recursive language. Therefore, since the Turing machine always halts, we can say that there is a membership algorithm for recursive languages and there is no membership algorithm for recursively enumerable languages. That is the main difference between these two, recursive languages and recursively enumerable languages. Okay. Now, after understanding this difference, now let's go to the theorem and see how to prove this. Now they are saying that if a language and its complement both are recursively enumerable, then the language is recursive. So what does that mean? Assume that this is sigma star. Sigma star means set of all strings possible. Okay. Let me write it here. Assume that this is sigma star. Sigma star means set of all strings possible, and let us say this is L. L is nothing but a language which is nothing but a subset of the set of all strings. Okay, and now they are saying that if a language L and its complement both are recursively enumerable. So what does that mean? Both for L as well as L complement, there are Turing machines which will say definitely yes for the strings which are present in the language, and if a string is not present in the language, they will be helpless. They might say no or they might fall in infinite loop. So understand this. Now if this is L, see, this is set of all strings possible, and out of which this is L, which is nothing but the language, and this is L complement. L complement is nothing but sigma star minus L, therefore this is L complement. Now they are saying that a language L and its complement both are recursively enumerable. That is what they said. So the language L and its complement both are recursively enumerable. Then what happens is we can design a Turing, it implies that actually there are two Turing machines, Turing machine 1 TM1 and Turing machine TM2. One is for language L and other is for language L complement, in such a way that if I give any string which is present in the language L to Turing machine 1, it will say yes, the string is present. That is the meaning of this. So whenever we say that there is a Turing machine for a language, what does it mean? It means that given any string in the language to the Turing machine, it will definitely say yes. But if you give it any string which is not in the language, we don't know. Maybe it will say no sometimes if you are lucky, otherwise it will fall in infinite loop, right? So to this, since L is given as a recursively enumerable language, I am assuming that there is a Turing machine TM1 in such a way that if I give any string to this TM1 which is present in L, it is going to say yes, the language is yes, the string is present in the language. But then the problem is, if I give it any string which is not present in the language, it might say no or it might fall in infinite loop, but I don't care about it now. Okay. And now L complement is also a recursively enumerable language. Therefore definitely there must be a Turing machine TM2, some Turing machine, to which if I give a language from L complement, which means which is not in L, it should definitely halt and say yes, the string is present inside the L complement, right? Now using these two Turing machines, what I'll do is I'll build a new Turing machine. What that new Turing machine will do is Now you give me any string in the entire sigma star, either it could be present in L or it could be present in L complement. You just give me one string, then I'll distribute it to both of them, then at least one of them is going to halt and say yes, isn't it? Therefore I got a new Turing machine TM3 by using a combination of these two Turing machines in such a way that you give me any string anywhere from sigma star, then I'll give it to them, both the Turing machines simultaneously, and both of them will start working. And since the string is going to be present in either L or L complement, because you cannot give it outside that, one of the Turing machine will definitely halt and say yes, which means wherever the string is, right? So if this one says halts and says yes, then I am going to say that yes, this string is present in L. If this one is going to halt and say yes, even though it is saying yes here, I'll just interpret it as no, right? Therefore if a string is present inside the language, I'm going to say that yes, it is present inside the language. If the string is not present inside the language, I'm going to say that no, it is not present inside the language, using the help of these two Turing machines. Therefore I got a new Turing machine which always halts. So whenever I get a reply from any one of them, I'm going to stop the main Turing machine. I'm going to stop both of them. So we are never going to follow infinite loop. So now I got a Turing machine which always halts whatever this string is, wherever this string is. Therefore the language L is recursive. So try to understand it. I don't know if you understood it or not. See, if the language L and its complement both are recursively enumerable, what does that mean? Both are having Turing machines independently, and those Turing machines are going to halt on any input given to them, if the input is in the language, isn't it? Therefore I assume that TM1 is the Turing machine corresponding to the language L, and TM2 is the Turing machine corresponding to language L complement. And by the definition, these Turing machines are supposed to halt if we give them any string which is present in the language. Therefore TM1 is going to halt for every string which is present in L, and TM2 is going to halt for every string which is present in L complement, and they are going to say yes, isn't it? Now I'll combine these two Turing machines into a new Turing machine in such a way that you give me any string, I am going to distribute it to both the Turing machines, both of them simultaneously. Then at least one of the Turing machines is going to say yes. So whenever at least one of them is going to say yes, you can stop both of them, which means we are not going to follow an infinite loop. If the TM1 says yes, then the output will be yes. If TM2 says yes, then output will be no. It is a simple complementation, isn't it? Therefore I got a new Turing machine which is going to halt for all the strings inside sigma star, and which is going to say yes, a string is present in L, or no, the string is not present in L, which is nothing but we even got the membership algorithm. A halting Turing machine is also a membership algorithm, isn't it? So this statement is right. If the language L and its complement both are recursively enumerable, then both the languages are recursive. So both L as well as L complement both are recursive. Now I have shown you that this is a Turing machine which halts for language L. Now if you just reverse the results, this one no and this one is yes, then you can say that this is the Turing machine for the language L complement. So both are recursive. And next point is, if L is recursive, then L complement is also recursive. That is the next statement. They are just independent. I hope that you understood this. Let me explain you the next statement. If L is recursive, then L complement is also recursive, and consequently both are recursively enumerable. So it is very easy to prove. They are saying that a language L is recursive, which means, let us say this is sigma star, and a language L is as always a subset of sigma star. And now they are saying that language L is recursive, which means for the language L there is a Turing machine which always halts. So what does it mean? Give it any string which is present inside the language L, it will say yes. Give it any string which is not present inside the language, it will say no. Already it is there, right? Then if language L is recursive, this is already there, this Turing machine is already there, then L complement is also recursive. They are saying that the complement of the language is also recursive. So what does that mean? How can you prove that? Now for the complement of the language, you should get a Turing machine which should say yes if the string is present in that, which should say no if the string is not present in that. then what I do is I'll construct a new Turing machine, let us say Tm new. Now this new Turing machine will act exactly the opposite way, which means whenever the original Turing machine said yes, you will say no, and whenever the original Turing machine said no, you will say yes. Now what happened because of this? So if the string is present inside the language L, then you are going to say no. If the string is not present inside the language L, then you are going to say yes. Anyway, you are going to halt on both the cases, and therefore this is the Turing machine which always halts for the language L complement. So we got a halting Turing machine for L complement also. Therefore L complement is also recursive, and consequently both are recursively enumerable. Why? Because recursively enumerable just wants a Turing machine. It doesn't care whether it halts or not. And now we have shown that both of them are having Turing machines. Therefore consequently both of them are recursively enumerable, isn't it? This theorem is very important, and proof is pretty simple. I don't know whether you understood it or not. If you didn't understand it, you please rewind the video and watch it 4 or 5 times. You are supposed to understand it. It is very straightforward. Okay, and now let me talk about this membership algorithm. So membership algorithm is nothing but, given a string, your machine should stop and say yes or no. You should not fall in infinite loop. For regular languages, your finite automata, give you a finite automata a string, it is always going to halt and say yes. Finite automata will never fall in infinite loop, isn't it? The reason is finite automata moves in only one direction, and by the time the entire string is scanned, it will definitely halt. It is not supposed to move left. Similarly, pushdown automata will also move in one direction, therefore it will definitely halt. So membership algorithm exists for finite automata, which means regular languages, and for context free languages, which means pushdown automata, and for context sensitive languages and for recursive languages. Only language which does not have membership algorithm is recursively enumerable language. The reason is the Turing machine may fall in a infinite loop. So keep that in mind. So membership algorithm is nothing but, given a string W, whether the string belongs to the language. This is nothing but membership algorithm. Now all the languages will have membership algorithm except only one language, which is recursively enumerable language. Got it? Okay. We have seen various types of grammars, various types of machines, and various types of languages. Now collectively on these languages, there are some few questions we could ask, like how these I'm saying that there is a let me draw the diagram, then you'll understand it better. I told you that there is one language which is enclosing everything, that is recursively enumerable language, which is nothing but set of all languages. This is nothing but set of all languages which are acceptable by or accepted by Turing machines. And now inside this, the set of all languages which are accepted by halting Turing machines is there, which is recursive language. And inside that, set of all languages which are accepted by linear bounded automata, which are called context sensitive languages. And inside that, set of all languages accepted by pushdown automata, which are called as context free languages. And inside that, set of all languages accepted by finite automata, which are called as regular languages. So we have all these classes of languages. Now the one interesting question which you could ask is this regular languages really a subset of context free languages? Which means, is there at least one language which is not regular, which is context free? If there is at least one language which is not regular, which is context free, then you can say that regular language is a proper subset of context free language. And for that, yes, we can say answer is yes. The language is a power n, b power n. A power n, b power n, n is greater than or equal to 1 or 0 is a language which is not regular but which is context free. Similarly, you could ask one more question saying that, is context free languages, set of all context free languages, a proper subset of context sensitive languages? Which means all the strings accepted, all the languages, is there any at least one language which is accepted by context sensitive or which is accepted by linear bounded automata, which is not accepted by a pushdown automata? And you can find out that yes, there is one language which is a power n, b power n, c power n. And now naturally To extend this question, you might ask, is there any language which is recursive and which is not context sensitive language? That is a difficult question to answer. In this sense, now I have given you some examples like this just to prove that yes, it is a proper subset. But then if you have to prove that there is a language which is recursive but not context sensitive, I cannot give you any such language like this, which means I cannot say a power n, b power n, c power n, or a power p such that p is a prime. Such kind of proof or language is not available for us. So in order to prove that, there are mathematical theorems which are used in order to say that, in order to prove that there is at least one language which is recursive but which is not context sensitive. So we don't have any language, or if you ask me to give us an example, I don't have any example, not anyone has. So proving it is a other case, which means they have used mathematical theorems to prove that there will be one language, at least one language, which is not context sensitive and which is recursive. That is what we could say. But then precisely writing that formal language is difficult. We can say that there exists at least one language and we can prove that, but then we cannot say what that language is because we don't have that. Okay, I mean, so, and again the same question is true here also. So if you ask me, is there at least one language which is recursively enumerable, which is not recursive? Answer is yes, there is at least one language, but then I cannot give you in this form a power n, b power n, c power n. So using the mathematical theorems, we can prove that these are all proper subsets of each other, which means this one is proper subset of this one is proper subset of this. But then we cannot say exactly what what that language is. And now next extension is, you might ask, next question you might be asked, you might have doubt is, yes, Turing machine is the most powerful machine in all the machines like finite automata, push-down automata, linear bounded automata. If you take all the machines, we know that Turing machine is the most powerful machine. Now the natural question is, how powerful is this Turing machine? So you might ask whether Turing machine is capable of accepting every possible language, which means if there are some languages, let us say set of all languages, I'll take all the languages which are possible. Now the interesting question to ask is Turing machine capable of accepting all these languages, which means for every language will there be a Turing machine? That is an interesting question. So in order to answer it, we are going to use the set theory. Okay, so the question is, I want to answer this question. For every language is there a Turing machine accepting it? It is a difficult question to answer. So for every language, do we have a Turing machine to accept it? Is a difficult question to answer it directly, but then we are going to use indirect proof to prove it. So I'll just give you a overview about what I am trying to do, and then I'll tell you in detail how to do it. Okay, giving you an overview will help you in understanding the concept better before getting into the actual concept. In order to answer it, what I'll try to do is, I'll show that the set of all Turing machines are infinite. The set of all Turing machines are infinite, and I'll show that the set of all languages are also infinite. This is set of all Turing machines and this is set of all languages. And then I'll show that, I'll try to prove that the number of Turing machines available, even though infinite, are lesser compared to the number of languages available. Both are infinite only, but then I'll prove that this is a bigger infinity and this is a smaller infinity. By showing that, we can understand that for every language, if you give one Turing machine, then we'll quickly run out of the Turing machines, and then there will be some languages remaining for which there will be no possible Turing machine. Remember, every machine can accept only one language. Therefore, if I have, let us say, 10 machines, I can accept only 10 languages. Similarly, if I have these many machines, I can accept only these many languages. Now it just indicates that there are some languages remaining for which we will never be able to give a Turing machine. Therefore, using this we can prove that Turing machine is not so powerful that it can accept everything. Therefore, there are some languages which are not even recursively enumerable. Recursively enumerable means they are not accepted by Turing machine. So, even the most powerful machine, Turing machine, is not capable of accepting every language. So, using this proof, using this argument, we can prove that. But then I cannot find out a language which is not accepted by Turing machine. That is not what I mean to say. What I mean to say is I'll use some methods or theorems using which I'll prove this. Now, in order to prove this, I'll talk about countable sets, uncountable sets, finite sets, infinite sets. Then I'll just build some mathematical theory gradually, one by one, step by step, and you please keep noting them down, and later slowly I'll prove this method. Okay. Now look at this. Sets are of two types. Sets means you know that already. Set is nothing but a collection of objects. I'm not going to define it. And sets is of two types. Again, we have something called as set theory, group theory. There I am going to discuss about sets in mathematics. But now I'll just discuss the part which I need in order to explain about the Turing machines. I am not going to discuss everything. Okay. Later we shall see it again. Now, sets are of two types. One is finite and other is infinite. Finite sets means if all you know that, okay, I'm not going to define. Finite means if there are countable number of elements like 10 elements, 20 elements or whatever. For example, if I have a power n such that n is less than or equal to 10 power 10 power 10, even though there are many elements, it is still finite. Okay, so you know what a finite is. I'm not going to define it. And now infinite means there is no upper bound. For example, a power n is greater than or equal to 1. If I have anything like this, a power n such that n is greater than or equal to 1, there is no upper limit, that is called infinite. Now coming to infinite, there are two types of infinite sets. One is countable infinite and other is uncountable infinite. So countable infinite is actually smaller infinite compared to infinite means there are lots of strings or lots of elements, and again in these lot of elements we can say that it is not too many and it is too many, which means if I say that a set is countable infinite, it means it is infinite but it is not too much. And if I say it is uncountable infinite, it is infinite and it is too much. If you try to compare a countable infinite set and uncountable infinite set, we'll see that we'll take it that countable infinite set is lesser compared to uncountable. So it is not right in writing like this, but then still this is the actual meaning. So you should not write it directly, but I am going to write it. It is the actual meaning, but don't write it anywhere. What I mean to say is finite set is less than, countable set is less than uncountable set. It is not given anywhere, but actually that is the meaning that I want you to understand. So finite set is less than, countable sets is less than uncountable sets. And now my main intention in talking about this entire theory is simple. I want to prove that set of all Turing machines are countable and set of all languages are uncountable. Therefore, number of Turing machines are less than number of languages. Therefore, there are some languages which are not accepted by any Turing machine. So, there are some languages which are not recursively enumerable. That is what I want to prove by the end. Okay. Now, before going ahead, given any set, how will you distinguish whether it is finite or infinite? That is very easy, straightforward. Now, once you found out that talking about finite sets is not very interesting because no one is interested in talking about it, but then talking about infinite sets is actually the most interesting thing. Now when we talk about infinite sets, we have to make distinction between two types. One is countable and uncountable. Given any set which is infinite, how can you say that it is countable, or how can you say that it is uncountable? That is the most important question. Now watch this. Countable set means a set capital S, any given set, is said to be countable if all the elements of the set can be put in one-to-one correspondence with the set of natural numbers. What do I mean by saying this is, if a set is given and if you take every element of the set and if you can give one element from the natural numbers to this one, and if you can arrange them all like that, then it is called as countable set. And what is uncountable set is, a set, obviously if a set is infinite and if it is not countable, definitely it is uncountable, isn't it? So instead of saying it entirely, which means if we cannot put in one-to-one correspondence with the set of natural numbers, what you could directly say is a set is said to be uncountable if it is infinite and if it is not countable. You can directly say that even. Okay, so I'll just take an example and I'll show you what I mean by giving one-to-one correspondence from the set, from all the elements of a set to all the elements of a natural numbers. See this, the definition says that a set is said to be countable if all the elements of the set can be put in one-to-one correspondence with the set of all natural numbers. It is, you might think that it is very simple definition, but then in order to actually apply this, it takes a lot of experience and practice. So I'll discuss about some of the examples using which you can answer any question in GATE coming to this topic, countability. Okay, so watch it once. Let us say, let us start with a small example, set of all even numbers. Let us assume that set of all even numbers is written like this: 0, 2, 4, 6, 8, 10, 12, so on. They are all set of all even numbers. Okay, and now I'll take set of all natural numbers. Set of all natural numbers are 1, 2, 3, 4, 5, 6, 7, so on. Fine. Now there should be one-to-one correspondence between every number here to every number here. If I can give that one-to-one correspondence, which means for every element in the set E, if you can give a element in the set N natural numbers, then I can say that set of all even numbers is countable. Okay, so how can I do that? We already did it, isn't it? So now for 0, the element given in natural numbers is 1. For 2, the element given is 2. For 4, the element given is 3. For 6, element given is 4. Right? Now how did we do that? So what is the procedure? So given any element, will there be a natural number? That is the question. So let us say the element given is 2i. So what is the natural number corresponding to this? I think for 2i, natural number corresponding to this is I plus 1, isn't it? Check that. For example, 2i, 2 into 1, 1 plus 1, 2 into 2, 2 plus 1, 2 into 3, 3 plus 1. Therefore, for any element of form 2i, we can give an element of form I plus 1. Right? So what can you understand from this? We can understand that for every element in the natural even numbers, we can give an element from the natural numbers as a correspondence. Therefore, we can say that this even numbers is countable since we are able to give it. So it is very straightforward for this example, but then it is not so easy to prove that some other languages or some other sets are actually countable. So let's just extend some of the I'll just explain you some of the terminologies used here. One is called index. Now element 0 is given element 1. Therefore, I call this number as the index given to this. This number as the index given to this. Therefore, every element is going to get an index, and that index is nothing but a number from the natural number set. So one other way of saying it is, if every element in the given set is going to have an index, then that index is nothing but the number to which it can be mapped to in the natural numbers. Therefore, you can say that such a number is such a set is countable, right? And this is how you can say that the set is countable, and every element is also going to have an index. So the element 2i has an index of I plus 1, isn't it? So if we can get the indices, then we can say that if every element is having an index, then we can say that the set is countable. One definition is, if you can put them in one-to-one correspondence with natural numbers, it is countable. Or for every element, if there is an index, which means the position at which it can be placed in the set, if you can say that, then also it is countable. Now let's see one more example. Let us say set of all odd numbers: 1, 3, 5, 7, 9, 11, so on. Now, can these elements be put in one-to-one correspondence with natural numbers? Check this. We can put them like this, isn't it? Therefore, for every element in this odd number set, there should be an element in the even number, in the natural number set. For the element 2i plus 1, what do you think is the corresponding index? So for the element 2i plus 1, for example, for the element 5, the corresponding element is 3. So how can you get this one? It is nothing but same as I plus 1. So for every element of the set of odd numbers of type 2i plus 1, the corresponding index we have is I plus 1, isn't it? Therefore, what can we say? Since we are having for every element one element in the natural number, there is a one-to-one correspondence between the elements. Therefore, the set of all even numbers is countable and the set of all odd numbers is countable. Okay. And now let's see one more example. The set of all real numbers. Real numbers means you can take any number, 0.1, 0.2, 0.3, anything, isn't it? Now, if you take set of all real numbers, the problem is just between 0 and 1, there can be so many numbers that they can all eat up the natural numbers available. Whatever natural numbers are there, I can generate so many numbers between these two that they can eat up all of them. Or you can come up with any method in which you will try to assign a number to that, but then it will all fail. Therefore, the set of all real numbers, see, the proving that set of all real numbers is this way. Between 0 and 1, we have so many numbers that they are capable of eating up all the numbers. Okay, so later I'll prove it in a concrete manner using some method called as diagonalization, but for now understand that just is an informal proof, just to understand for your understanding sake. It is informal proof. Later I am going to give you a formal proof. What I mean to say is, only between 0 and 1 we have lots of numbers that all these numbers have the capacity to eat up all the numbers of natural numbers. So only between these two, if we eat up all the natural numbers, what about the remaining numbers on the number line scale? Real numbers means everything, isn't it? Therefore, we cannot actually give one-to-one correspondence between real numbers and natural numbers. Therefore, set of all real numbers is uncountable. Remember this, I'll give you the proof later. So the proof for even numbers is countable and odd numbers is countable is, for every element I have given you an index. For every element 2i, the index is I plus 1. For every element 2i plus 1, the index is I plus 1. Therefore, if you are able to give an index, that is nothing but a correspondence in the natural number. That is how I am able to prove that they are countable. But then for these real numbers, I will not be able to come up with any index. Now, I will just use some other proof. This one-to-one correspondence is okay. You can prove it this way, but then it is difficult to prove it for all the sets that they are countable. We shall use some other better methods to prove that a set is countable. Okay, I'll tell you what they are now. Using the previous definition for countable sets, like putting one-to-one correspondence from all the elements of a set to natural numbers, it is very confusing, which means for some sets it might look as if we can easily put them in one-to-one correspondence, and for some sets it might look as if we cannot put them in one-to-one correspondence, and in both the cases you might go wrong. So by using the definition which is given in textbooks, some of the textbooks, that previous definition, it is very difficult to say whether a language is countable or not, whether a set is countable or not. Therefore, I have framed this new definition, and using this you will be able to understand this concept very easily, and you will be able to answer any gate question, and you will be able to prove the rest of the things very easily. So I framed this definition. You please read it and make a note of it, and it is right, and anything that you want to prove as countable can be kept in this form. Okay, I'll read it out and I'll explain you this, and then I'll take examples. The previous examples which we have seen, the set of all even numbers, odd numbers, we shall again examine them in the light of this definition, and then we shall see how we could use this one in order to prove that set of all Turing machines are countable, which means set of all Turing machines are infinite but less, and then we shall prove set of all languages are uncountable later. Okay, so just watch it once. A set is said to be countable. A set is said to be countable if there exists an enumeration method using which all the elements of the set can be generated for any particular element. Okay, let's go step by step. A set is said to be countable if there exists an enumeration method using which all the elements of the set can be generated. This means that if you are given a set, then you should be able to write a kind of algorithm or program, but then I am not saying that it is an algorithm because it need not stop. So you just give a method using which we should be able to generate all the elements of the set one by one. You give me a method, okay, using which all of them are going to be generated. And then for any particular element, which means given any element, if you follow your method, it takes only finite number of steps to generate it. If that is the case, which means, try to understand it, I'll give you an infinite set. What you should do is, you should come up with a method or a procedure, or we should not call it an algorithm. Calling it as a method or procedure is right, but then don't call it as an algorithm because it need not stop. It could go on infinity, but then what is required is you should be able to write it down as a method. Now that method should be able to generate all the elements of the set one by one. And now given any particular element, I should be able to reach that element using your method in a finite number of steps. Now if you can give me such a method, then the language is said to be countable, then the set is said to be countable. Okay, so come up with a method, given a set, generate it, which means generate all the elements. Enumerate means write it down, every element, writing every element one after one is enumeration. And now enumeration method means we are writing a method which will write down all the elements one after the other. Now your method should write down all the elements one after the other. Then what I need is, I want this method so that all the elements have to be generated, so that all the elements can be generated in any particular way. And if any particular element is given, I should be able to reach it in finite number of steps. If such a method is given, then I can call that the set is countable. And the finite number of steps that are required, that are taken to generate an element, which means given an element, you are able to generate it in finite number of steps, right? That finite number of steps which are actually taken in order to generate that element can be used as its index, which means you can call that number as the index. Now once you get the index, that is nothing but a mapping into the natural numbers, isn't it? Once we get an index, that is nothing but the mapping into the natural numbers, isn't it? So it is simple, very simple. So definition is very simple, and I'll just take the example, and then I'll show you how to use this definition to prove that a set is countable. Now as an example, let's say set of all even numbers. Set of all even numbers. Now you come up with a procedure using which you will be able to generate all the even numbers, and then using your procedure, if I give you any element, you should be able to reach that element in a finite number of steps. If we can do these two things, then I can say that it is a countable, right? So how can I generate set of all even numbers? You can just write a for loop, isn't it? Maybe I can write like this: for I equal to 0 to infinity. It is not an algorithm because we are going to infinity. What is an algorithm? You should always stop in finite number of steps. But since I is going from 0 to infinity, we are never going to stop in finite number of steps, isn't it? For I equal to 0 to infinity, if I write like generate means just print to I. So this is the enumeration method, right? So now if I write like this, what will this enumeration procedure do? It will try to generate all the numbers one after the other. Like first it will generate 0, then it will generate 2, then it will generate 4, then it will generate 6, then it will generate everything. Therefore we found out an enumeration method using which we will be able to generate all the elements. But then it is not just enough. Just finding out the enumeration method is not enough. What you should do next is, you should be able to generate a given number in a finite number of steps. For example, how many steps does it take to generate 0? 1 step. How many steps does it take to generate 2? 2 steps. How many steps does it take to generate 4? 3 steps. 6, 4, 8, 5 steps, so on. Therefore, every element can be generated after fixed number of steps. What is the implication of that? Now these number of steps can be used as the index for this particular element. Therefore, for every element I found a natural number, isn't it? That natural number is the index itself. Therefore, I can say that the set of all even numbers are countable because there is a one-to-one mapping to the natural numbers. We found the one-to-one mapping without actually doing that original definition. See, you might feel that this method is long and it is difficult, but then later you'll understand that with other examples this is the easiest method rather than putting one-to-one correspondence to natural numbers. Okay, now let's see how to do this with the set of all odd numbers. Now we found out that set of all even numbers are countable. Now let's see what to do with the set of all odd numbers. Set of all odd numbers. It is simple. For I equal to 0 to infinity, you generate I plus 1, then 2i plus 1. Then what will be generated? Initially 1 will be generated, and then 3 will be generated, 5, 7, 9, 11, so on, right? And what about the index? This will be generated in one step, this will be generated in 2 steps, 3 steps, 4 steps, 5 steps, so on, isn't it? So every element can be generated in these many steps. Therefore, these are nothing but the indices for these elements, and since every element has got an index, and one more thing, for a particular index there will be two elements will not be there, which means 2 elements are not going to be mapped to one index. In one step we are generating only one element, therefore every element will get a different index because at every step only one element is going to be generated. So this particular element can be used as the mapping into the natural numbers. So for every element of the set we got a mapping into the natural numbers. So we can say that set of all odd numbers is also countable. What about set of all real numbers then? Set of all real numbers, it is very difficult to come up with an enumeration method first. So you cannot generate all the real numbers using an enumeration method. Maybe you might try to generate it, but then later you will not be able to reach a particular element. Let us say you are trying to generate all the real numbers, but then if you start with 0.0, then 0.01, then 0.001, then 0.0001, this procedure itself will never stop, because if I start with 0.01 and then 0.1, 0.01, 0.001, this procedure itself will never stop and it will go on, keep on going for infinity, and you will never reach a element starting with 1.0. Therefore, even though it is not an actual proof, we shall prove this later. I'll prove that the set of all real numbers are not countable later using some other method. But for now, just understand that giving a enumeration method and then generating an element in fixed number of steps for real numbers is impossible. Therefore, it is uncountable. Let's examine some other examples. Now let's examine one more interesting language. I want to see whether the set of all quotients of form P by Q, the set of all quotients of form P by Q, where P comma Q are positive integers. So let us say P comma Q are two numbers which are positive integers, and now we have set of all quotients of that form. Now what I would like to see is whether all these numbers of this form are countable or not. That is what I wanted to see. And in order to do this, let's observe how to do this. So if all the numbers are of form P by Q and if they are all in a set, is that set countable or not? So what we should come up with is, first of all, how will that set look like? Let us say that is set S. That set will look like this: 1 by 1, 1 by 2, 2 by 1, 1 by 3, 1 by 4, 3 by 4, so on. There will be lots of elements like that. Okay, and these are all the elements, and now we want to find out whether this set is countable or not. So how can we find out whether a set is countable or not? You try to find out a enumeration procedure or a method, meaningful way, in which you can generate all the elements of the set, and given any element that should be reached in a finite number of steps, and that number is going to be the index into the real numbers, natural numbers. Therefore you can say that is natural. Now let's see what could be the enumeration method. Let us say I want to generate all the numbers in one order like this. I'll want to do it 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, so on. Now what is the problem with this? It is enumeration method. It is able to generate all the numbers, or it is looking like as if it is going to generate all the numbers, but then it is not a enumeration method which we wanted. The reason is, if you go on enumerating the numbers like this, the number 2 by 1, that will never be generated. The reason is, there will be infinite number of numbers which will be having numerator as 1. 1 by 1, 1 by 2, 1 by 3, it will keep on going, and using this method you will never come across the number 2 by 1. Therefore, given this number 2 by 1, you will never be able to generate it in a finite number of steps. Why? We are going to go infinite times, and then sometime we will come across this, and we don't know when. We have infinite numbers. So we failed to find out enumeration method. So failing to find out enumeration method, is that going to be the proof to say that it is not countable? No way. If you are not able to find a enumeration method, it doesn't mean that there does not exist some other enumeration method using which you could enumerate it. Okay, so it is not actually true to say that since we are not able to find a particular enumeration method, the number is not, the set is not countable. In order to say that set is not countable, you should do some other proof explicitly proving that the set is not countable. We cannot use such an argument. That is invalid. Now, but then how can we prove that a set is countable? By finding out an enumeration method, we can say that the set is countable. But then, without finding an enumeration method, we cannot say that the set is uncountable. For that, the proof is different. Okay. Now, let's try to see, is there any other way I could enumerate the strings? Therefore, I could enumerate the elements. Therefore, I could, generate a particular element in a fixed number of steps. If I have 2 by 1, if I take this method 2 by 1, 2 by 2, not 2 by 1, let me say, other method is I want to increase the numerator, which means 1 by 1, 2 by 1, 3 by 1, 4 by 1. If I go on like this, again I get infinite number of numbers, isn't it? But all of them are going to have the denominator as 1, and you will never be able to reach the number 1 by 2. Therefore, even this enumeration is also not the valid one which we wanted. Then we want some other meaningful method using which we will be able to generate every particular string in a fixed number of steps. So maybe if you could think for some time, you could come across this, many ideas. I'm going to tell you one of them. You might come across some other ideas, but I'll tell you one of them. So one good idea is, don't go either in the increasing order of numerator or in the increasing order of denominator. What you do is, just add numerator plus denominator, and you go in the increasing order of the sum. So if numerator is p, denominator is q, you add p plus q, and now go in the increasing order of p plus q's. For example, here in this case, what is the smallest number? 1 and 1. Therefore, the first sum is 2. So only number possible is 1 by 1. The sum is 2. And the next sum possible is 1 and 2. Therefore 3. So what are the various numbers possible which are having a sum of 3, adding up numerator and denominator? One is 1 by 2 and other is 2 by 1. So go in the increasing order of sum of p and q, and inside a particular sum, go in the increasing order, which means both these numbers are going to have the sum as 3, but then go in the increasing order, which means 1 by 2 is less than 2 by 1. And what is the next number? 4, isn't it? What are the numbers of p by q form which have the sum as 4? 1 and 3, 2 and 2, and then 3 by 1. These are the 3 numbers possible, isn't it? Next one is 5. So what are the numbers which will have 5? 1 and 4, and you can write it down, so on, right? So using this method, if I enumerate all the strings, all the elements of the set, then for any given element, we can say that it will be generated after these many steps. Therefore, every element will get an index, and that index is going to be mapping into the natural number. For example, index for this number according to this enumeration method is 1, and index to this number is 2, and index to this number is 3, this number is 4, 5, 6, isn't it? Therefore, if given any number like 3 by 1, we can say that after 6 steps I will be able to reach it. After first step this is generated, second step, third step, fourth step, 5 steps, 6 steps. Therefore, every element, we can say that every element could be generated after fixed number of steps, and that finite number of steps is going to be the index for the element. And now that element, that index could be used as the mapping into the natural numbers. Therefore, the set of all these numbers, the set of all these numbers of form p by q are having one-to-one mapping with the natural numbers. If you see that this is nothing but the one-to-one mapping with the natural numbers, right? Therefore, we can say that the set of all numbers of form p by q are countable. Remember this. Now let's see set of all strings generated by any alphabet. Let us say alphabet sigma equal to a comma b. This is the alphabet given, and what can you say about this set containing all the strings which are possible over sigma, which means sigma star. The set which contains all the symbols possible over a comma b is sigma star. And what are all the elements present in this? Epsilon, a, b, aa, ab, ba, bb, so on, isn't it? They are all the strings, and definitely it is infinite. Now we want to find out whether it is countable infinite or uncountable infinite, and what does that depend on? Whether you will be able to come up with a enumeration method. Now let's see what method you want to use. So let us say for some time you forget about epsilon, and let us say it is like all the set of all strings are nothing but, every string is nothing but a word, English alphabet word, English language word. Then if you follow the dictionary order, what happens? In dictionary order you could write them in one order, definitely all the strings. Now if you follow the dictionary order, what happens is maybe the first element will be a, and the next element will be aa, next element will be aaa, and all these a's will be like this forever. The problem with this enumeration is, with this type of ordering is, if you follow this type of ordering, you will never come across the word starting with b or simply b. B can never be generated in finite number of steps. Therefore, this method, this ordering fails. Therefore, we want some other clever ordering using which we will be able to generate every string even if it is starting with b. So, some other enumeration order which you could use is, maybe you could pause the video and you could think for some time. So, what you could use is, you could go in the increasing order of lengths, which means you could generate all these strings of length 0. Therefore, epsilon will be generated. Next, you could generate all the strings of length 2. So, what are all the strings of length 2? A and B, and inside a particular length you could use a dictionary order. The reason is, inside a particular length there are finite number of strings. So, if there are finite number of strings, you can use dictionary order so that you can reach any element in a finite number of steps. So, inside this string lengths of 1, I can arrange them in dictionary order, which means A and B. And now, inside string lengths of 2, I can again use dictionary order, which means AA, AB, BA, BB. And again inside strings of length 3, I can again use dictionary order. AAA, you get 8 strings, right? AAB, ABA, so on, BBB. So now using this method, if you generate every string possible, then what happens is, this one will be generated in 1 step, this one can be generated in 2 steps, this can be generated in 3 steps, 4 steps, 5 steps, 6 steps, so on. Every element in this set can be generated in fixed number of steps. You can give me any number, I can generate in a fixed number of steps. I mean, you can give me any string, I can generate in a fixed number of steps. For example, if you ask me to generate AAB, for example, then after how many steps I can generate it? 7, 8, 9. Therefore, every element is going to get an index, and that index is nothing but mapping into the natural numbers. Therefore, since every number has got a mapping into the natural numbers, we can say that this set is countable. So, the set of all strings possible over any alphabet is actually countable. You can extend it to any alphabet, not just a comma b. The set of all strings possible over any alphabet is always countable. It has a very important implication, and this result is so popular, and this enumeration method is so popular in the this theoretical world that they have even given this a name. So if you use this particular ordering, it is also called as proper order. Proper order. Proper order means going in the increasing order of string lengths, and then within the string lengths we can sort them out, isn't it? That is called as proper order. So proper order is very popular, and it has even got a name. This enumeration is very popular, it has even got a name. Now let's see, if a set is countable, there are lots of implications on this. Okay, so if a set is countable, then what can we say? I'll just see what to do this, how to do. So now you understand that the set of all strings possible over sigma equal to a comma b are countable. And now there is one more important rule, that every subset of countable set is either finite or countable. It is very interesting, which means if a set is already known to be countable, if you take a subset of it, then that is also countable. This particular property has very important implications. I'll just discuss them shortly, but then just understand how it is right. Now I am saying that a set is countable. A set is countable means this particular set S is countable, then this set is having one-to-one correspondence between all the elements and the set of all natural numbers. This is what I mean to say. Already this set is having one-to-one correspondence with the set of all elements in the set of natural numbers. And now if I take a subset of it, subset means I'm taking some subset small s, then subset means only some of the elements will be here. Now already these elements are present in this set, therefore there will be one-to-one mapping between this particular element and the particular element that is already present in this. For example, if in this set S, I am going to choose a number or I am going to choose an element from this set capital S and place it here, I will just put a one-to-one correspondence between those two numbers. Now for every element already there is an image here. Image is nothing but itself. Try to understand it. Already a set is said to be countable, therefore it is having one-to-one correspondence with the set of all natural numbers. For every element in this set, there is one natural number in this set, which is set of natural numbers. That is what the meaning of countability is. So now what is that I am trying to do is, I'll just find out, or I'll just take a subset of elements of this set. Then what happens is, I am getting some elements in this set, and for every element, how did I get this element? Because that element is already present in this set, isn't it? Therefore I'll put a one-to-one mapping between the element chosen and its image there. Image means the same element. Then what happens is, already I have one-to-one mapping from the subset to the set, and already there is a one-to-one mapping from the set to the natural numbers. Therefore by composition, that is called composition, we shall discuss it in functions. By composition rule, this set is also countable. Therefore every subset of a countable set is countable in case if it is infinite. In case if it is finite, it is simply finite, but then we are not interested in this. We are not interested. So every subset of a countable set is either finite or countable. So this point is very important. Okay, now we already found out that sigma star over any sigma is countable, which means set of all possible strings is countable. And now a language is nothing but subset of this. Every language till now we have seen is nothing but a subset of sigma star, which means either you take a power n, b power n, or a power n, b power n, c power n, or whatever it is. Every language is a subset of this set, and this set is already known to be countable. Therefore every language is countable. Understand it? every language is countable. I am not talking about number of languages. Given a language, that is definitely countable, which means all these strings in a language can be put in one-to-one correspondence with the natural numbers. Okay, so every language is going to be a countable language, or it is going to be finite language. Okay, write it somewhere. Now look at this question. Let us say sigma equal to 0 comma 1, which means alphabet is only zeros and ones, and now sigma star, the set of all strings possible over sigma is sigma star, which is epsilon 0 1 0 0 0 1 1 0 1 1 so on, right? And now this set is also nothing but this set. Sigma star is also countable. The reason is already we have seen that if sigma equal to a comma b, sigma star is countable. Just you replace 0 with a and b 1 with b, then we get the same language, and we can use the proper ordering and we can prove that it is countable. And now we know that this sigma star is countable, and we already know that every Turing machine can be encoded as a string of zeros and ones. You please refer to that topic where I did it. I think in the topic of universal, when I was talking about universal Turing machine, I told you how to convert a Turing machine into a string of zeros and ones. Now this set sigma star is countable, isn't it? And now second thing I know is, first thing I know is sigma star is countable if sigma equal to 0 comma 1. In fact, any sigma star is countable. And now the second thing I know is every Turing machine can be encoded as a string of zeros and ones. This one also I know it. So these two things I know. One thing is sigma star is countable. Second thing is every Turing machine can be encoded as zeros or ones, zeros and ones. Therefore, set of all Turing machines is nothing but set of all strings of zeros and ones, isn't it? Third thing is I can say that set of all Turing machines, let me represent it as S, is a subset of sigma star. Just try to understand this point. Now if I encode every Turing machine as a string of zeros and ones, and now if I list them all in one set, that set will definitely be a subset of this. Or you can take this sigma star and you can take each string one by one, which is generated by enumeration method, and then you can check whether a given string can be a valid Turing machine or not. If it is a valid Turing machine, you can take it. If it is not a valid Turing machine, you throw it. Then whatever strings I get into S, that is definitely a subset of sigma star. Now what can you say? So using these 3 points, what we can say is, and we already know that, one more point I am just adding it, you already know that point, but just I am adding it. Now every subset of countable set is either finite. If it is not finite, it is countable, isn't it? So we know that set of all Turing machines, they are not just finite, they are infinite. But then what kind of infinite? Countable infinite. Therefore, using this rule, we are able to find out that the set of all Turing machines are countable. Okay, so this point therefore using all these points, I hope that you are writing them down. Therefore using all these points, we can say that set of all Turing machines are countable. Using all these points, I can derive this. So this point has lot of implications. Okay, now we know that. Okay, so if you understood it, I'll derive more points on that. You please note down all these points. Now sigma star, if sigma equal to 0 comma 1, then sigma star is countable. This one we have already proved it. And next one is every Turing machine can be encoded as a string of zeros and ones. We did it when I discussed about the universal Turing machine. And next one is set of all Turing machines is a subset of sigma star. Why? because if you write down all these strings of zeros and ones, they are nothing but they belong to the sigma star only. Therefore there is subset, and we already know that every subset of countable set is finite or countable. This one also we have already seen. Therefore from all these points we can say that set of all Turing machines are countable. Now this particular point is going to have lots of implications. Now we shall see what those implications are. Okay. Now knowing that set of all Turing machines are countable is going to lead us to many implications. Now what are the results we get out of it is, since we already know that, watch it. Now Turing machines are countable. Let me say C is the shortcut to represent that Turing machines are countable. Then what does this imply? Then how many our Turing machines are there? There will be those many recursively enumerable languages. Therefore, since the number of Turing machines are countable, the number of recursive languages are countable, isn't it? Therefore, recursively enumerable languages, not recursive, recursively enumerable languages are countable, isn't it? Now what does this mean? If recursively enumerable languages themselves are countable, so we can say that a recursive language is a subset of recursively enumerable language. Therefore the number of recursive languages are countable. RL means not regular, it is recursive languages. Recursive languages are countable. Now context-free language is a subset of recursive language, isn't it? Sorry, context sensitive language. Therefore context sensitive languages are countable, and push down order that context free languages are again subset. Therefore context free languages are countable, because every subset of a countable set is countable, and we know that all these languages are like Russian dolls. If you open Russian dolls, you know that if you open a doll, inside that there will be one more doll. If you open that doll, inside that there will be one more doll, isn't it? Like that, inside that language everything is contained. So therefore if the main language is countable, then already the languages which are present inside it as a subset, proper subset, are already countable, isn't it? So context free languages are countable, therefore regular languages are countable. Everything is countable. All the languages, either you say the number of recursively enumerable languages available, they are countable. Everything is countable. And next implication is, if you look at the hierarchy of these Turing machines, these machines, Turing machine is the biggest machine, and all the machines are present inside it. And what we could say about all this is, now see, the better solution will be, instead of talking about the languages directly, the better idea would be the other one. So for every language there is a Turing machine, isn't it? So every recursively language if number of Turing machines are countable, every recursively enumerable language is countable. Okay, the set of all recursively enumerable languages, and direct implications will be like this. So we can say that every Turing machine is a push-down automata is, you can modify a Turing machine in such a way that it can act as a push-down automata. Therefore, if Turing machines are countable, then push-down automata are countable. The reason is, we can modify a Turing machine in such a way that even though it is having the input tape, instead of using it as a tape, if it could use it as a stack. Therefore, if Turing machines are countable, then push-down automata are countable. The reason is, push-down automata are a slight modification to Turing machine, isn't it? And now if we know that even LBA is also a slight modification of Turing machine. If already Turing machines are countable, then a subset of the machines which are supposed to use only that restricted stack, they are also countable. Therefore push-down automata are countable, and finite automata is nothing but a Turing machine which is restricted in such a way that it has to use only finite amount of memory on the tape. Then finite automata are also countable. So everything we know of as of now are all countable because of this rule. Okay, but then even though the number of languages are countable, see this, one important thing is, even though all these languages are countable and the machines are countable, we didn't prove that the set of all languages are countable. Okay, so I'm not trying to confuse you, it is a bit confusing, so you please rewind the video over and again and listen it. So what I didn't prove yet is I didn't prove that the set of all languages possible are countable. I didn't prove that. Actually, the set of all languages possible are uncountable. Now, the set of all Turing machines or any number of machines possible is countable, and the set of all languages possible is uncountable. Therefore, there are some languages for which there are no machines at all, which means there are some languages which are not even recursively enumerable. Okay, we shall prove it later, but for now these are all the implications which we got from this. Okay, now let us assume that an alphabet is given sigma equal to a comma b, and it can be extended to any other alphabet a, b, c or 0, 1, 2, anything, but assume that one alphabet is given sigma equal to a comma b. Now we know what is sigma star. Sigma star is set of all strings possible over a comma b, and we already know that sigma star is countable. And now what we could prove is 2 power sigma star. 2 power sigma star is nothing but set of all subsets of sigma star, which is nothing but set of all languages possible. We can prove that 2 power sigma star is uncountable. So how we could prove is, I am going to show you the proof now, and how they have proved it initially is, there is a scientist by name Carter. He has given a method called as diagonalization, using which he made a statement and then he proved that statement. But even though I am going to prove it, I will just write it in terms of some other statement, and again we shall come back to this. So this point, no, you already know. If sigma equal to a comma b, sigma star is countable, you already know. So how do we know that sigma star is countable? Because we are going to have a proper order. So whenever we have proper order, that is nothing but enumeration, so that is countable. And now you don't know how to write how this is right, which means 2 power sigma star is countable. How is that right? We don't know that yet. Okay, but then what I know is okay, first going before proving it, let's see what the original proof is, what the original theorem is, and then how they have converted that theorem to this one and they have proved it. Okay, so the original theorem is like this: if a set S is countably infinite, which is nothing but countable, then they say that 2 power S is uncountable. This is what they have proved. So even proving this or proving this, both are same, but coming to TOC, it is better that I will take the first statement and prove it, or you can even if I prove the second statement, it can imply this first statement. The reason is, in place of S I am going to put sigma star. Already we know that sigma star is countable, then 2 power S is uncountable. It follows from the proof. Either you can take first one or second one. I am taking the first one because we are talking about TOC. Okay, so in TOC we are talking about sigma and languages and sigma star, everything. This will be easy for you to understand. That is why I am taking it. Anyway, there will be no difference. There will be not much difference. And before going ahead, you should understand this representation 2 power S. 2 power S is nothing but set of all subsets, which is also called as power set. So I'll just take a small finite example and I'll show you what a power set is, and then we shall go ahead. See this. Now if S equal to a finite set, I'm not talking about this theorem, I'm just explaining what a power set is. If S equal to a comma b, then what will be 2 power S? Set of all subsets. What is set of all subsets of this? One is empty set is a subset of that, and then a singleton set is a subset of that, and then everything a comma b is a subset of that. Therefore set of all subsets is containing 4 elements, all these 4 elements. So that is what the meaning of power set is. So if a element is, if S is countable infinite, which means if there are infinite number of elements here, then the set of all subsets is nothing but you are going to take some elements of this and we are going to form the subsets. That is the meaning of it. Okay, so now let's just first discuss about that statement. Anyway, you could take down the 2 statements. Now whatever I am going to prove is going to be the proof of these 2. Okay, so this is just an example. Now I want to prove that if sigma equal to a comma b, which means input alphabet is a comma b, then we already know that sigma star is countable. Now I want to prove that 2 power sigma star is uncountable. So first of all, if sigma equal to a comma b, what will be the elements of sigma star? You know that sigma star will contain epsilon a, which means set of all strings possible, a b, you can write them in any order, no problem, ab, ba, so on, or let me just extend it, a, so on. Okay, these are all the elements of sigma star. Sigma star contains all these elements. Now we can represent any subset of sigma star as one element of 2 power sigma star. So the elements of 2 power sigma star are nothing but subsets of this set. Okay, now how do I represent a subset of this is, for example, one element of 2 power sigma star is, first of all, you know what 2 power sigma star is, right? It is nothing but set of all subsets of sigma star, which is nothing but set of all languages possible. Okay, now one language, let us say, is a, b, a. Then how can I represent this language is, I could say if element a is present, then I am going to represent it with a vector. In the under a I am going to put 1, which means, see, in this set epsilon is not present, therefore it is going to be 0, a is present, therefore it is going to be 1, b is present, therefore it is going to be 1, a is present, therefore it is going to be 1, and no elements are present, therefore all are going to be zeros. So every element of this set 2 power sigma star can be represented as a string of zeros or ones, zeros and ones. So every element is going to be represented like this. Let us say I have an element like this, epsilon and ba, that's it. Then how can I represent it as a string of zeros and ones? Then epsilon is present, a is not present, b is not present, a is not present, ab is not present, ba is present, this is not present, so on. So I can represent every element of 2 power sigma star, which means every language, as a string of zeros or ones. Okay, so what has happened now? Now I am representing every language like this. Now what I do is, I assume that 2 power sigma star is countable. So I initially assume that 2 power sigma star is countable. Therefore if a set is countable, we know that every element in that set is going to get an index, and depending on that index I am going to put all the elements in one table. So try to understand it. Now I am assuming that the first assumption is 2 power sigma star is countable. If a set is countable, we know that it can be mapped, it can have a one-to-one mapping with natural numbers, which means every element in that set is going to get an index, and using that index I am going to put all the numbers, I am going to put all the elements in one table, and the table is going to look like this. So let us say every element is kept in its corresponding index 1, 2, 3, 4, 5, 6, so on, and the elements are like this. Just every element, every possible element. It can be anything. I am just taking this as example. Something like this. So now every element of this set are now placed in a order fashion, in an orderly way, using the indices of the elements, because the set is a countable set, because I am assuming that the set is a countable set. So all the elements have been written in the table. So every element should definitely get, if an element belongs to the set 2 power sigma star, that should definitely be present in this table at some point, at some index. So either here or here or here. Okay, that is the assumption. So all the elements have their indices, and according to the indices I have written all the set, all the strings in the table. Now it is going to be infinite length, this way and that way. Anyway, my assumption is I have written all of them. Then what I do is, I'll take the diagonal elements. I'll take the diagonal elements like this, the entire diagonal, the main diagonal, and then what are the elements in the main diagonal? You see that the elements in the main diagonal are 0, 0, 0, 1, 0, so on. Now what I do is, I'll just complement this 1, 1, 1, 0, 1, so on. Now I'll get a new element. This element is not present in the set, definitely. The reason is, this element cannot be the first element, because it is differing with the first it is differing with the first bit of the first element. this element cannot be the second element because it is differing with the second bit of the second element. This cannot be third element because it is differing at least in one point. It cannot be fourth element because it is differing at least in one point. Therefore, whatever we got, the newly got string that is not present already in the table, therefore our assumption that the original language is, or the original set is countable, is wrong. Okay, so what can we say? 2 power sigma star is uncountable. It is actually, the proof is very simple. Maybe it will be difficult for you to understand in one go. You please rewind this video and again watch it. Anyway, I'll just give you the summary like this. See, I'm saying that sigma star is set of all strings. So I'm going to write the sigma star entirely here, and every element, every language is nothing but a subset of this. Therefore, every language can be written like this. Every language can be written like that. Language can contain a string, or it may not contain a string. If it doesn't contain a string, I am going to put a 0. If it contains a string, I am going to put a 1. So now I assume that the set of all languages, which is nothing but 2 power sigma star, are countable. Now according to the definition of countability, if a set is countable, all of the elements are going to get some indices. Now my assumption is that yes, all the elements have got some indices. According to their indices, I am going to order them in a table, just in a table from top to down. Then if I do this, every element which is present, every language which is present in 2 power sigma star should occur at some point at some index, isn't it? So all the languages should be there in the table. That is what is right. That actually that is right if our assumption is right. What is our assumption? That it is countable, right? Now I have taken the main diagonal elements, and now I got a new new language by just complementing this, and that new language cannot be first language or second language or third language, because that new language differs with every language in at least one bit, isn't it? Therefore, I got a new language which is not already present in our table. Therefore, my assumption that all the languages are present in the table at some index is wrong. Therefore, my assumption that the entire set is countable is wrong. So what did we get finally? Finally, we got that the set 2 power sigma star is uncountable. Okay, it is very important. So what can we say now? The set of all languages possible are uncountable. We have already seen that the set of all Turing machines are countable, but the set of all languages present are uncountable. So what could you say? The number of Turing machines are less than the number of languages. So there must be some languages, or at least one language, or definitely there will be some language. So there must be some languages which are actually not recursively enumerable language, or Turing machine is not so powerful that it could accept every possible language, which means there will be some languages for which there will be no Turing machine. Why? Because every Turing machine can define only one language, and now we have more languages compared to the Turing machines. Okay, so maybe if you didn't understand it, you could write all the points one by one. First point is, I am assuming that 2 power sigma star is uncountable. Therefore, every element of 2 power sigma star can be placed in the table, and every element will be placed exactly at some index, isn't it? Then every element is already present in this. Then I later found out that I have got a new element which is not already present. Therefore, my assumption that all the elements are present in this is wrong. So my initial assumption that it is countable is wrong. Therefore, it is uncountable. So what is the implication we got? Set of all Turing machines are countable, and set of all languages are uncountable. So what could we say? There are some languages for which there is no Turing machine. This is Turing machine which is countable. This is set of all languages which is uncountable, 2 power sigma star. Therefore, there are some languages which are not recursively enumerable. So the reason is simple. Every Turing machine can define only one language. So if I give one-to-one mapping, then all the Turing machines will be over too soon, and then there will be many languages remaining for which there will be no Turing machine. Got it? So outside these recursively enumerable languages, there will be even more languages. Okay, so this is how we could prove it. And one more way of saying this same statement is, if S is a countable set, if S is uncountable set, then 2 power S is, if S is countable set, then 2 power s is uncountable. It can be proved in the same way. How? You just write all the elements of s and then you represent every element of 2 power s as a string of zeros or ones, and you do the same assumptions and do the same thing. In place of sigma star, if you replace s, we get the same thing, right? And using this method we can prove that real numbers are also uncountable. Maybe you could work it or not on that. So how we could do it is, maybe you can try to write all the real numbers in a table, and then you take the diagonal of this and you just complement the diagonal, then you get a new element, and definitely that element is not in the table. The same way, see, simple, you write all the diagonal, all the real numbers in some order in the table, and then you take the diagonal, and whatever element is there, you just take the 9th complement. 9th complement means 9 minus that number. Then you suddenly got a new number which is not already in the table. Therefore you can say that set of all real numbers are uncountable. So if you want to prove that anything is uncountable, the best method is diagonalization. If you want to prove that anything is countable, the best method is that enumeration. You find out enumeration method. Got it? So now using this you will be able to answer any gate question. Okay. See these statements about the countable sets. These statements I am going to give you proof in informal way, and these questions there is a chance that they might ask you as a theory, like true or false questions. Therefore they will not ask you the proof, but still I will give you some proof to some extent. Okay, so what you could do is you could write down these points and then possible by heart it, or at least see or try to remember them somehow. Or proofs are very simple. I'll just give you the proofs. If S1 and S2 are countable sets, then S1 union S2 is countable, which means if you have two countable sets and if you apply union to that, then it is also countable. So how is it possible is, S1 and S2 are already countable, which means there is a enumeration procedure which will generate all the strings of S1 and S2. See this? Now already S1 is countable and S2 is countable, which means there is already a enumeration procedure available which can enumerate A1, A2, A3, all the elements of S1 like this, and all the elements of S2, B1, B2, B3, which is already able to enumerate all the elements like this. Now we are saying that S1 union S2, which means if I apply union these two, the resulting elements, whatever I get, they are also countable. That is what we should prove. Then simple, what we do is run the enumeration method of S1 to one step and generate A1, and run the enumeration method of S2 to one step and generate B1. Therefore resulting enumeration method is nothing but combination of these two enumeration methods. Run the enumeration method for S1 for one step and generate A1, and run the enumeration method of S2 for one step and generate B1. Therefore every element will be generated like this: A2, B2, A3, B3, so on. So any element can be generated after finite number of steps. If you want B2, initially if it is 2 steps, now it will be 4 steps. That doesn't matter. Only thing what matters is every element of the set can be generated after some fixed number of sets. Therefore S1 union S2 is again countable. In fact, you could apply this method to any number of sets, to a finite number of sets, which means if S1, S2, S3, so on Sn are all countable sets, you can apply union to all S1, S2, so on union Sn, and we can generate all the elements in a enumeration procedure, which is actually a combination of enumeration procedure for S1, S2, so on Sn. Similarly, you can extend this. That is what I mean to say, right? And next one is S1 cross S2 is again countable. So if S1 and S2 are countable, S1 cross S2 is also countable. That is what we have to prove. So what you could do is, if S1 and S2 are already countable, then all the elements have already got their indices, isn't it? 1, 2, 3, 4, 5, 6. All the elements have already got their indices, right? Then what you do is, you just add 2 indices, go in the increasing order of indices, which means, okay, how to prove it is, do you remember how we have proved that quotients, set of all quotients of form P by Q? Same method you can apply here. So there the P by Q both are numbers, therefore we have taken the sum of P plus Q, and then we have gone in the increasing order of P plus Q, and for a given P plus Q we have sorted it out, isn't it? The same method can be applied here. So what you could do is, Since we are not sure that S1 and S2 contains only numbers, it could be any other elements. So already S1 and S2 are countable, therefore the elements are like this: A1, A2, A3, A4, so on, and then B1, B2, B3, B4, so on. Then you could give them natural numbers 1, 2, 3, 4. Why? Because they are the indices, right? So every element is going to get a natural number. Now you just replace every element in S1 and S2 with their corresponding indices. Then what you do is go in the increasing order of these natural numbers like this. First you generate all these numbers, then you give them the corresponding natural numbers, then go in the increasing order of the sum of these natural numbers, which means now if you take that the sum is 2, then what is the only combination possible? 1 1. 1 1 is nothing but A1 B1, and what is the next sum? 3. So 3 means 1 2 and then 2 1, isn't it? Therefore what do we get? The element A1 B2 and the element 2 1 is nothing but A2 B1, right? Therefore we get every order pair at some point. And next the sum is 4. 4 means 1 3 2 2 3 1, isn't it? So you can go on like this, and 1 3 is nothing but A1 B3 and 2 2 is nothing but A2 B2 and 3 1 is nothing but A3 B1. So like this you can generate all the elements in some order. So even if you don't remember the proof, just remember that if two sets are countable, then their cross product is countable. If two sets are countable, then their union is countable, and the union can be extended to any number of finite sets, as well as cross product can be extended to any number of finite sets. See this? That is what they are saying. It can be extended to any number of countable sets. Cross product, the previous one, it can be extended to S1, S2, S3, so on, anything. How? The same method can be used, isn't it? So the starting point is, since they are countable, they already have enumeration method, therefore I am using that enumeration method to be used as enumeration method for the resulting set. Got it? And now the set of all languages that are not recursively enumerable is uncountable. It is somewhat interesting question. Maybe they might ask you as a true or false. See, one more thing, they didn't ask you all these difficult questions till now. All the questions which are asked in GATE are very simple. I am going to solve all of them, and these are the difficult questions which I am trying to solve. They might not ask them in GATE, but still knowing them will give you an advantage in case if they ask you. Okay. Now, the set of all languages that are not recursively enumerable is uncountable. So we know that the set of all languages can be partitioned into two sets: the set which is recursively enumerable and the set which is not enumerable. We know that set of all languages is nothing but 2 power sigma star, isn't it? Now this 2 power sigma star can be partitioned into two sets. It is set of all languages. One set is countable. Why? Because it is recursively enumerable. These are all set of languages which are recursively enumerable. Since Turing machines are countable, this set is countable. So the set of all recursively enumerable languages is countable. Now we don't know about the other set. This is the set which is containing languages which are not recursively enumerable. We don't know anything about it. Just assume that this is countable. If we assume that this is countable, then the entire set is a union of two countable sets. Therefore it has to become countable, but then we already know that 2 power sigma star is not countable, therefore this is not countable. Okay, I don't know if you understood it or not. See, again let me explain you. What I mean to say is, the set of all languages is nothing but 2 power sigma star, set of all subsets of sigma star, that is set of all languages. Now out of these languages, some languages are already recursively enumerable. How? If there is a Turing machine for a language, then that language is recursively enumerable, and we already know that the number of Turing machines are countable. Therefore number of languages in the total languages which are recursively enumerable are countable, and that will be equal to the number of Turing machines. Therefore one part of this set which is recursively enumerable, which contains set of all languages, which means in this slide all these languages are recursively enumerable are already countable. Okay, now the remaining set we don't know about it, so I am just assuming that the remaining set might be the set which is nothing but the set of all languages which are not recursively enumerable is, I'm just assuming that is countable. Then what happens to the resulting set? The resulting set is a union of two countable sets, therefore that should be countable. How? By using this rule. The union of two countable sets is again countable, isn't it? If that is true, then our initial proof that 2 power sigma star is uncountable is a failure, but then that is true, isn't it? Therefore our assumption that it is countable is false. So the set of all languages which are not recursively enumerable must be uncountable, which means there are infinite number of languages which cannot be accepted by Turing machine, and that infinity is uncountable infinity, very large. Got it? Okay. Let's talk about computability and decidability. Actually, both computability and decidability are same. In the sense, both of them talk about whether there exists an algorithm or not. Okay, before going ahead, let me explain you what an algorithm is, and let me show you what the difference between Turing machine and algorithm. Okay, so algorithm is, it is nothing but a Turing machine, but this Turing machine is supposed to halt. So if for a problem there is an algorithm, it is as good as saying that for that problem there is a Turing machine which is always going to halt. But then if you have a Turing machine, it is not actually an algorithm. The reason is algorithm is supposed to halt after finite number of steps or after some number of steps, but then Turing machine is never going to halt. Therefore only halting Turing machines are considered as algorithms. Okay, and now you already know that Turing machines are countable, so I'm just extending this concept. You already know that Turing machines are countable, isn't it? And therefore halting Turing machines are a subset of Turing machines, and I already told you that every subset of a countable set is already countable. Therefore halting Turing machines should also be countable. So halting Turing machine is nothing but an algorithm. So what did we find out now? Even the algorithms are also countable, but then we found out that the number of languages are uncountable. Every problem can be compared to a language. Okay, so now the number of problems are uncountable and number of algorithms are countable. Therefore what could we derive? That there are some problems for which an algorithm might not exist. Okay, so let's talk about what is the exact meaning of computability and what is the exact meaning of decidability. I hope that you understood what an algorithm and Turing machine is. From now on I am going to use wherever if in order to say that there is an algorithm, I can even say that there is a Turing machine which halts, or in place of Turing machine which halts, you can put an algorithm. Okay, now let's see what is the difference between countability and decidability. Actually both the concepts are very identical, or sometimes both of them are used in place of each other with a minor difference. Okay, whenever we talk about a function, so whenever we talk about a function, like let us say f of n equal to n square plus 1. So what is the meaning of it is, if you give it some n, it is going to compute this value. So given an input, if it is going to compute some output, then that is called a function. Now if there is a algorithm to compute a function, then such a function is called computable. Okay, so if there exists an algorithm, or what is an algorithm? Turing machine which halts, isn't it? If there exists an algorithm or a Turing machine which halts, which takes this input and then produces this output. In terms of Turing machine, how can I write it is, if there exists a Turing machine to which if the input is given on its tape, then again it is going to produce the output on the same tape, and then it is going to halt for every input given is called a then that function is called computable. Okay, so what is the definition of computability is, if there is a function which is defined on a domain. So what is the domain for this? F of n, let us say the domain is set of all numbers, set of all integers. Then what about the range? Range is nothing but set of all a subset of positive integers. Okay, so given a function and a domain, domain means from which set are you going to pick up the input. Given a function and the domain, if there is a Turing machine which will produce the output on the tape, given that input on the tape, it should produce the output on the tape, and it should definitely halt for every input chosen from the domain. Okay, domain is very important. So once you fix up a domain, and if for all the inputs from the domain, if your Turing machine is definitely going to halt with the output on the tape, then we can say that such a function is computable. It is very simple. See, in simple words, what it is let us say you have a function. Okay, let us say the function could even be not just this one, the function could even be a problem. I don't want to use the word problem, but then just think of it like this. We want to sort all the numbers. Now all the numbers are given to the Turing machine. They are all on the tape, and now the Turing machine should try to sort it out and then keep them in ascending order. Then that is also a function. A function is going to take a set of natural numbers, and then it is going to produce a set of natural numbers. Therefore domain and range both are natural numbers. So if your Turing machine is able to solve that function for all the inputs coming from your domain, and it is definitely going to halt, then such a function is called computable. Okay, and coming to decidability, we just want to simplify the things. So very often talking about functions and then giving some proofs is somewhat difficult. It is not impossible, but then it is somewhat difficult. Just to simplify the things, we are more interested in rather than functions, we are more interested in problems. So what is a problem is a statement whose output will be either true or false. And now our whenever we, for example, a problem can be like this. Classic problem is n, a number n, a prime? You just have to find out is m a prime, which means here you are not actually taking the input and then producing some output. Here you take an input and you just say one thing, either yes or no. If 3 is given, if n is given as 3, you say yes. If n is given as let us say 10, you say no. Alright. So if you have such a problem whose answer is either yes or no, and if there is an algorithm or a Turing machine which should definitely halt for all the inputs from the domain. So here domain is, let us say domain is set of all natural numbers. Set of all natural numbers. Okay. Now when do I say that a problem is decidable is if for a problem there exists an algorithm or a halting Turing machine, both are same, which will take anything from the domain, which means it will take any input from the domain and which will say either yes or no correctly, and it should halt. If you have such a machine or such an algorithm, then we can say that that problem is decidable. So decidability is very easy to apply compared to computability. It can be shown that we can convert a problem from computability to decidability and then think about this, or give some proof whether a problem is decidable or not. Okay, so what we are interested in is either in TOC or in algorithms. Rather than talking about computability, we will talk about decidability. We will take a function and we somehow convert it into a yes or no problem, and then we try to find out if there is a Turing machine which can answer that problem. In case if there is a Turing machine which can answer that problem, we can say that there will be a Turing machine which can compute it. It is straightforward. Therefore we are not interested actually in the functions, we are interested in the problems. Okay, so what I mean to say is whenever we have a domain, okay, and now given any input from the domain to a Turing machine, that Turing machine should definitely halt and say yes or no for such a problem if you can find such a Turing machine, or if there exists such a Turing machine. If we can prove that there could be such a Turing machine existing, then we can say that the problem is decidable. Okay, simple. So function means, computability means we talk about function and there should exist algorithm or halting Turing machine. and decidability means we are talking about a problem which is nothing but yes or no answer, and if there exists algorithm or Turing machine which halts, then we say that it is decidable. So computability and decidability both are actually same, but only difference is when we talk about the function and when we talk about the problem. I hope that you understood it. And one more thing you should be very careful is every time a problem, whether it is decidable or not, that should depend on the domain, because given a single instance it is always decidable, isn't it? So for example, given a single instance it is always decidable. Simple. So how can I prove that a single instance is decidable is, let us say you have given me some problem. Okay, I'll just talk about a problem which is undecidable, which means we cannot give a generic algorithm for that, and then I'll tell you that for a given instance we can find a see, it is somewhat difficult to understand, so you please pay more attention here. Now there is one example, classic example. Example is a given grammar capital G is ambiguous, which means given a grammar you should find out whether it is ambiguous or not. Okay, and now let me say the domain is set of all context free grammars. So actually this problem is undecidable. Okay, I know I'll just talk about this problem shortly after some time, but then this problem is undecidable, which means there is no algorithm or there is no halting Turing machine which can say that a given grammar capital G is ambiguous. This problem is ambiguous or see. So how is it a problem is, now you give a specific instance or specific grammar and you put in place of G, the answer should be either true or false, isn't it? So the statement will be either true or false depending on what the input is, but the domain is set of all context free grammars and this problem is undecidable. Later I'll show you how to prove that it is undecidable, but for now assume that it is undecidable. Now if the domain is not set of all problems, if I give you only single instance, which means I am just giving you domain is not this, I am just giving you this particular grammar G1, is it decidable or not? This is definitely, this particular grammar G1, is it ambiguous or not? So answer is definitely it is decidable. The reason is you could find a Turing machine which will always say yes or which will always say no. Now if this grammar is actually ambiguous, now you can give this Turing, now there exists a Turing machine which will say yes, isn't it? So it is very difficult to understand this, but just pay attention here. See, I am saying that if the domain is very large, sometimes some problems might go undecidable, but then if the domain is a single instance, which means given a grammar, if you are asking whether it is ambiguous or not, I am saying that it is decidable. Why? There has to be a Turing machine which should say yes or no, and then it should definitely halt. Now what I take is, I'll just produce a small Turing machine which will always say yes, and then I'll say that there exists a Turing machine which will say this, or I'll produce a Turing machine which will always say no, and in case if the answer for this one G1 is not an ambiguous grammar, then I'll say that for this problem there is a Turing machine, therefore it is decidable. So just keep this point in mind, that a particular instance of any problem is always decidable, but then when it is applied to a common domain, it might be decidable or undecidable. For that we need to prove. So it is very important, just write it somewhere. Any particular instance of a problem is always decidable. Any particular instance means given a particular grammar G1, whether it is ambiguous or not, it is decidable, because you can give a Turing machine which always says yes or which always says no. At least one of it is going to be the answer, isn't it? So very important point, given an instance of a problem, it is always decidable. Why? Because there always exists a Turing machine. What is a Turing machine? Take a Turing machine which always says yes, or take a Turing machine which always says no, whatever the input is. Now at least one of that Turing machine is going to be the Turing machine for this instance, isn't it? That is how we can prove it. But then given over a range, then that depends, right? So now in TOC, our main concern is will be given many problems, and now we should be able to say whether that problem is decidable or not. So in order to do this, we use a trick, we use an indirect method. So finding out whether every problem is decidable or not, it's somewhat difficult. So what we do is we find out one problem which is undecidable. Okay, let me just show you this in terms of writing. Hope that you have taken everything, and whatever I speak, you please note them down also. You keep pausing the video and writing it. Okay, these are all very important. And what happened is in GATE for the past 2-3 years, before 2-3 years they didn't focus much on the Turing machine decidability, countability, but then I think they have used up regular expressions, regular languages, context-free grammar questions so much that I think they are out of the questions. Therefore they are now focusing on a new topic. See, and one more thing is previously before 5-6 years, this particular GATE question paper, the number of aspirants used to be less and the coaching used to be not so good. Therefore even for a moderate kind of question, it was very difficult for many people to answer them. But now with these many coaching centers and with this lot of effort going on, people are able to answer many questions very easily. Therefore the standard of the GATE examination is going to be increased. So if they have to ask a difficult question in TOC, the only topics which will be suitable will be Turing machines, or decidability, undecidability, countability. So these are very, very important. Even in algorithms also we have the same concepts. So I feel that in GATE 2015 they are going to definitely touch more questions from PNP, decidability, undecidability, and then Turing machine. So I'll be discussing about Turing machines in depth, so that even if they ask you a very difficult question, you will be able to answer it. Okay. So what I would like to tell you is, whatever I speak, even every single word, you please pause the video and keep noting them down. It is very difficult for me to write everything on the board. It is not that if there is something on board you should write it. Write everything that I am speaking, so that you will be able to easily understand it later or easily refer to it later. Now let me tell you one important, very, very important point here. This is going to be very important even when you discuss algorithms. Now, how can we prove that a problem is undecidable? I'll talk about something called as convertible. So if there is a problem P1 and if there is an algorithm or a halting Turing machine which can convert it to a problem P2, which means there is algorithm, okay, and now if there is an algorithm to solve problem P2, which means there is an algorithm, this P2 is decidable. See, now there is a problem P1, I am able to convert it to problem P2, and now problem P2 there is an algorithm. Then I can say that for problem P1 there is an algorithm. Therefore if P2 is decidable, then P1 is decidable. How? First you convert the problem P1 to P2 and then you solve P2. Therefore since we are able to solve P2, it is nothing but the answer for P2. Now the conversion should work in such a way that the answer to P2 should also be an answer to P1. Okay, I'll just repeat it again. See this, if there is a problem P1 and there is an algorithm to convert it to a problem P2 in such a way that if the answer to P1 is true, the answer to P1 should be true, which means whatever answer I get here, that should even be the answer to P1. If there is a conversion algorithm like that, and now there is an algorithm to solve P2, it is as good as saying that we got an algorithm to solve P1. Then what is the algorithm? Conversion algorithm plus solving algorithm. Now this procedure is called reducibility. Reducibility means converting one problem to other problem in using a algorithm or a halting Turing machine. Now if you find out that this problem is decidable, then definitely this problem is decidable. Okay, so I'm just writing it. See this, if P2 is decidable, then P1 is decidable. Under the conditions, what are the conditions? There has to be algorithm to reduce every instance of problem P1 to an instance of problem P2, and there has to be algorithm to solve problem P2. Therefore, if there is a reduction algorithm and then there is a solving algorithm for P2, then we can say that if P2 is decidable, which means if there is a solving algorithm for P2, then P1 is decidable. If we can solve P2, it is as good as solving P1. Okay, and it is very straightforward. I think you will understand it, but the next point is somewhat difficult to understand, so just try to understand this. Now, if it is already known that, if it has been already proven that, or it has been already proved that problem P2 is undecidable, problem P1 is undecidable, and now there is a polynomial time conversion to problem P2, definitely problem P2 cannot be decidable. Okay, so try to understand this. If P2 is decidable, P1 is decidable, but before this, if it has been already proven that the problem P1 is undecidable, which means there is no algorithm or Turing machine, it has been already proven, then definitely P2 should be undecidable. The reason is, in case if P2 is decidable, then it actually conflicts with our proof that P1 is undecidable. Okay, these 2 points are very, very important. Okay, so if there is a polynomial time conversion from, or not polynomial time conversion, we shall talk about the time later. If there is an algorithm or a halting Turing machine which can convert every instance of problem P1 to some instance of problem P2 in such a way that answer to problem P2 is also an answer to problem P1, and if there is an algorithm or halting Turing machine which can solve P2, then we can say that P1 is decidable, which means if there is a reduction algorithm from P1 to P2, and if P2 is decidable, then P1 is decidable. This is straightforward, isn't it? Now, the second point is very important. If P1 is already proven to be undecidable, it is already proven to be undecidable, then definitely P2 must be undecidable. Why? The reason is, if P2 is decidable, then it turns out that P1 is decidable, which actually conflicts with our already existing proof that P1 is undecidable. Therefore, P2 should definitely be undecidable. So, how do we now from now on, how can we prove that a problem is undecidable? Is, see, this particular point is given wrong in every possible book. In every possible local addition book you take it, in every possible gate question they solved it, this point is completely given wrong. Okay, if you want to learn about it, please read these standard books like Ullmann. There they have given it right, but then don't read them, you will not be able to understand this. Just follow my lectures, I am going to cover everything possible. Okay, now what I am trying to say is, in order to prove that a given problem is undecidable, so what you should do is, try to find out first a Turing machine. If it is not possible, you cannot say that if you fail to find a Turing machine which halts, or if you fail to find an algorithm, you cannot directly say that it is undecidable. There should be a rigid proof. Now, for that reason, already there is a one small problem or one basic problem which has already been proved to be undecidable. That problem is halting Turing machine. That is also called as halting problem. I'll discuss about it shortly. Now there is already a basic point or basic problem which everyone knows that it is undecidable. Okay, that is nothing but halting problem. Now you take this halting problem and then you give it to you convert it to any problem, any given problem at hand, then we can say that it is undecidable. And now you take this problem and you convert it to any other problem, then you can say that it is undecidable. So that is how undecidability is decided. Okay, I mean undecidability is found out. So given any problem, First you start with the halting problem, convert it to some other problem, convert it to some other problem. Whatever you get on the way, all these problems are undecidable. Okay, so the starting point for the theory of undecidability is halting problem. Now I'll show you what the halting problem is. We shall discuss about it, and then we shall see how to prove that various other problems are undecidable based on this one. Okay. Turing machine halting problem is the most interesting problem in computer science. The reason is, this is the basic point which is used to prove that other problems are undecidable. And in early 1900s, the scientist and the professor Turing has found an interesting scenario. So what happened is, he is a professor and he is having many PhD students, the students who are doing PhD under him. And actually the requirement for a PhD is, you are supposed to publish at least 5 papers, or I think 3 papers if it is related to the same area, and it is 5 papers if it is chosen from various random areas, which means if you are working in the same area, same topic, 3 publications are enough, international publications, and if it is in different areas, 5 are required. So what happened is, he is having lots of PhD students, and whenever he see them, actually they all seem to be very busy. So always they are very busy working, but then no one is graduating, which means no one is publishing papers or no one is leaving the university. So because obviously you know the reason, the university life is the best life, and they got addicted to that cool job, cool life, because they will be getting the stipend, they need not do anything, they have to go to lab, sit there and then come out, there are no deadlines, anything. Therefore he got confused, what should I do? I mean, it is not, they are never halting, they are always busy computing, but they are never halting. So should he wait for more time, or should he stop them? Isn't it? That is a kind of Turing machine halting problem, isn't it? So what he did is, he tried various methods, like he said that after 6 years, if you are still in the university and if you didn't finish your PhD, I am going to stop your stipend. And then he removed from their computers all the video games, everything he tried, but then nothing seemed to work. Then what happened is, he tried to persuade them using some other means. He started sending them mails saying that there are attractive jobs in the industry if you finish PhDs. But even that plan also backfired. The reason is, they had to go there and work in order to get the money, but here they are getting the money without anything. So I mean, even if it is not for money, they need not work, they can just stay in the campus and in the lab, and they have a cool life. So they are never going to graduate. So then he found out that this problem can never be solved, no one could solve a problem. Now in present scenario, if anyone joins a PhD, there is no guarantee that he is definitely going to halt and get the PhD degree. Similarly, so how he has framed this Turing machine based on that idea is, this Turing machine halting problem is, given a Turing machine, some Turing machine from the domain of all Turing machines, and given a string to that Turing machine, will that Turing machine ever halt and say, yes, this I accept this string, or no, I don't accept it? And now it has been proven to be undecidable, which means there is no way anyone can come up with an algorithm which can say that a Turing machine will ever halt. So it is undecidable. I'll just explain you the statement, and then I'll show you the theorem which is used to prove that this problem is undecidable. It is very straightforward. I'll just go step by step. You please note down whatever I speak. Okay. Now see this Turing machine. Given the description of a Turing machine M, which means some Turing machine M is given and an input word and an input W. To that Turing machine, some input is given, does capital M when started with W, which means if I start the Turing machine with the input as W as its input, ever halts. So what does it mean? So the question is, given a Turing machine and an input to that Turing machine, will that Turing machine ever stop and say yes or no? That is the question, and it has been proved that we cannot decide it. This problem is undecidable, which means there is no algorithm as of now discovered which can say whether a Turing machine will halt or no. So how to prove it? See this, the theorem. This is very interesting theorem. You'll love it. You'll love this. See this. If the halting Turing machine were decidable, which means if the halting problem is decidable, So what does it mean? If there is an algorithm which can say whether a Turing machine halts or not. What is an algorithm? Some other Turing machine, isn't it? If there is some other Turing machine which can halt and say whether this particular Turing machine can halt or not, okay? If it is decidable, then every recursively enumerable language would be recursive, which means if that is so, if it is decidable, then every RE is recursive. What is the main difference between recursively enumerable language and recursive languages? Membership algorithm, isn't it? Which means for recursively enumerable languages, there is no membership algorithm, but for recursive languages, there is definitely membership algorithm. What does that mean? Okay, I'll just talk about it shortly. Let's finish this theorem. If the halting Turing machine were decidable, then every recursively enumerable language would be recursive. What is that? If it is true that halting Turing machine is decidable, then the recursively enumerable languages and recursive languages both would be same. Consequently, the halting problem is undecidable. It is undecidable that because we have already proved that the recursive languages and recursively enumerable languages are different. Okay. So which means I'll just go step by step. Now we already know that the main difference between recursively enumerable languages RE and the recursive languages is this. Here, if there is a Turing machine, then that language is called recursively enumerable. Okay. And what about recursive? If there is a Turing machine which halts for every input, then it is recursive. So what is the main difference between these two statements is, given a recursive language, we never know, given a recursively enumerable language, we never know whether, given a string and, okay, 1 second. Let's see this. The difference between the recursively enumerable language and recursive language is, if there is a Turing machine, then it is recursive language. If there is a Turing machine which halts, that is recursive language. So what does it say is, now here I have a Turing machine and given a string W, it will say yes, I accept it, in case if the string W belongs to the language, or it might say no sometimes, or it might go into infinite loop. That is the meaning of it. Therefore, whenever you ask the question, does W belongs to the language, that is called membership algorithm. So that is called membership question. So whenever you ask that problem of membership, does given string belongs to the language, our Turing machine might never halt. Therefore, that membership algorithm is undecidable for the recursively enumerable language, which means the main difference is here I don't have any membership algorithm, no membership algorithm. Even though I explained it once, I am again doing it because maybe I will use a different set of words and different set of statements which might help you in understanding the concept, in case if you didn't understand it earlier. That is why if there is a difficult concept, I'll try to touch it even 2-3 times so that you will understand it better. Okay. Now coming to the recursive language, given a string W, it means that there is definitely a Turing machine which will halt and say yes, this string belongs to the language, no, this string does not belong to the language. What does that mean? For this one, the membership algorithm always exists, and for this one there is no guarantee that there is a membership algorithm. Why? Because our Turing machine might go and fall in the infinite loop. So the main difference between these two languages is, one language contains membership algorithm and the other language does not contain membership algorithm. And moreover, it is very easy to observe that recursively enumerable languages are subset of recursive languages are subset of recursively enumerable languages. Why? Because the basic definition for recursively enumerable is if there is a Turing machine, and for recursive languages if there is a halting Turing machine. Therefore, by definition itself, every recursive language is recursively enumerable. Okay. Now, even there is a proof saying that there is at least one language here, which is recursively enumerable, which is not recursive. I didn't give you that proof because it is very difficult to understand and it is not required for GATE and it might be very confusing. So I didn't give you that, it is not very important. But then remember that there is already a proof saying that there is at least one language which is recursively enumerable and which is not recursive. Therefore, recursively enumerable and recursive languages both are different, or this is the actual scenario. You cannot say that all recursively enumerable languages are recursive, because there is at least one language which is recursively enumerable and which is not recursive. And now this theorem is saying that if halting a problem is decidable, then every recursively enumerable language would be recursive. But already we have proved that every recursively enumerable language is not recursive. Therefore, definitely halting problem must be undecidable. Okay, how to prove it? I'll just prove it now. Now see, the theorem proof is not yet over. I'm just revising what are all the points required to prove this theorem, and you know all these points already. In case if you don't know them, please make a note of them now. Okay, so two basics are recursively enumerable languages and recursive languages. The main difference is there exists a membership algorithm for recursive but no membership algorithm for recursively enumerable. In case if we can prove that for all recursively enumerable languages there is a membership algorithm, then we can say that recursively enumerable and recursive languages are same. But then we have already shown a proof that earlier someone has already proved that there is at least one language which is recursively enumerable which is not recursive. So now the entire concept boils down to a single point. Now you just prove that recursively enumerable equal recursive by using this statement. What is the statement? If halting problem were decidable. If you prove that, then under this assumption, then we can prove that this assumption is wrong. Okay, just see how we can prove it. Let us assume that a language L is recursively enumerable. A language L is recursively enumerable. Then definitely there exists a Turing machine M which accepts all strings which are present in the language, and it will say yes if the string is present in the language, and it will say no if the string is not present in the language. Okay, but then we don't know whether the Turing machine halts or not. Got it? So now this Turing machine M is such a way that it will say yes, I accept this string, or it will say no, I don't accept this string, or it might even fall in the infinite loop. Now let us assume that this halting problem of the Turing machine is decidable, which means there is other Turing machine or algorithm which will definitely say yes, this Turing machine halts or not. Okay, now let us say the input, see, this is sigma star and this is the language L, and now we have a Turing machine M. I'm giving you diagrams also so that maybe you'll understand it better if you're not understanding by my words. And now if I give any string from the language to this Turing machine, it will say yes, this string belongs to the language. If I give any string W, if I give any string which is outside the language, then this Turing machine may say no sometimes, or it might fall in infinite loop. This is the problem, right? That is why there is no membership algorithm. Now if there is an algorithm, which means if the halting problem is decidable, then there would definitely be an algorithm which can say whether this Turing machine, in fact any Turing machine, can halt on a string or not, right? Then what I do is, before giving to this Turing machine any string, I'll just give that Turing machine to the algorithm. Why? Because there is an algorithm, there is one such algorithm. So I'll not directly give the string to the Turing machine. Whenever you wanted to give a string to the Turing machine, then what I do is, before giving that string to the Turing machine, I am going to give it to the algorithm, right? Now that algorithm is going to take that Turing machine M and this string W, and it is going to say yes, it halts, or no, it does not halt. In case if it says that yes, it halts, which means yes, the Turing machine M halts on W, then I really take that string and I give it to machine M. I really take that and give it to the machine M, the string W. Then what happens is, I wait for some time and it definitely halts, and it will say yes it is there or no it is not there. In case if the algorithm is saying that no, the machine does not halt on W, then I will directly say that no, this string does not belong to the language, isn't it? Therefore, I have an algorithm which will definitely halt and say whether a string belongs to the language or not. Therefore, what happened to this language L, which is a recursively enumerable language, has got a membership algorithm. Therefore, every recursively enumerable language must be recursive, which actually contradicts with our earlier proof that there is at least one language which is recursively enumerable which is not recursive. Therefore, what can we say? Halting problem is undecidable. Got it? So I don't know if you really understood it or not, but I tried to make it very simple. Okay, what you could do is please rewind the video and watch it again. I'll just go through these steps once again. See this? Now what I mean to say is, L is a recursively enumerable language. Then there must be a Turing machine M which will take any string and it will say yes if the string belongs to the language, or it will say no if the string does not belong to the language, or sometimes it might fall in infinite loop in case if it does not belong to the language. That is the problem. Now if the decidable problem is, if the halting problem is decidable, then there must be an algorithm which will be able to take any Turing machine and any string, and it should be able to say that yes, the Turing machine halts, or no, the Turing machine does not halt. Then what is that I am trying to do is, given this Turing machine M, I'll take the word W and I'll not give the word W to M directly, the string. What I do is I'll give it to the algorithm and then I'll ask it whether it halts or not. In case if it halts, which means if it says this yes, then I am going to take this string and then give it to the machine, and then I am going to say yes or no. Got it? And now in case if it doesn't halt, then I am going to say no. Okay, if you didn't understand it, I'll just give you a metaphor so that you'll understand it. So it is like this. Now before, you don't know whether a PhD student is going to finish his PhD or not. Now if the halting problem is decidable, it means that there must be some procedure available during the selection process. When you recruit that, when you give a seat to the PhD student, then there must be some procedure available during the recruitment which says whether a student will be able to finish his PhD or not. So before taking the student, which means before giving the string to the machine, we ask that procedure, which means we ask that particular person who is able to decide whether he could finish the PhD or not. We'll ask him whether he will finish the PhD or not. If he says yes, he is capable of finishing the PhD, then only I'll take that student and then I'll give him some time, and then he either finishes or he will leave the institute. Okay, and now if there is that person is saying that no, he will never finish this PhD, he will just stay there and he will just stay in the institute and he will never leave the institute, or he never finishes the PhD, then what I do is I will not give him this seat and I will initially say no. Therefore that actual original Turing problem, that PhD problem, has been decided. But then if you have such a procedure, now we got that every recursively enumerable language is recursive, which is contradicting the proof that there is a recursively enumerable language which is not recursive, right? Therefore what we could say is our halting problem is undecidable. Okay, I don't know if you really understood it or not. At least remember one point, that halting problem for Turing machines is undecidable. Okay.